Hello, and welcome to Sleepy Science. I'm so glad you've found your way here tonight. Whether you've come with a mind full of questions, a heart in need of calm, or simply a love for drifting into sleep with the quiet company of the universe, you're in the right place. Tonight, we'll take a slow, gentle journey from the universe's first heartbeat to the lives of the stars that made us possible. We'll step into the darkness before the first light, witness the birth of the very first elements, and follow them as they weave themselves into planets, oceans, DNA, and everything you've ever touched. We'll meet ancient suns that burned for only moments in cosmic time, yet left behind the stardust that became our bones. From the silent glow of the cosmic microwave background to the impossible legacies of the first stars. This is the story of where we came from, told in the soft language of science and wonder. Nothing too loud, nothing too fast, just the quiet unfolding of time, matter, and meaning. Before we begin, I'd love to know, where in the world are you listening from tonight? Are you wrapped in a blanket under the hush of evening, or leaning back in a chair with the sky outside your window? If journeys like this soothe you, or if they spark something deep inside, please do like the video and tap subscribe. It truly helps other curious, sleepy minds find their way here. Now, take a slow, steady breath, and let's drift back to the very first moments of everything. Journey to the darkest moment of the universe. You don't reach the universe's darkest moment by closing your eyes. You reach it by learning a different way to pay attention. Because this dark is not an empty room but a quiet stage between two kinds of light. A hush after the first glare fades, and before the first stars learn how to shine. And if you imagine the whole cosmos as a long night's journey, this is the hour when the house lights are down, the curtains are drawn, and the actors have not stepped out yet, though you can feel them breathing just behind the fabric, long before you and me, long before the familiar glow of constellations. Space was filled with a simple, thin mist of the lightest gases, spread everywhere like fog after a storm, and nothing in that mist burned. Nothing cackled, nothing called attention to itself. Yet everything important was slowly getting into position. Because gravity was gathering, time was stretching, and the stage was being set for the first fire. To understand why it is called the darkest moment, think about how your eyes work. They need bright sources to see shapes. And without lamps, a room looks blank even if it is full of furniture. The universe at this time, it was not empty. It was just unlit, its stuff too cool and too smooth to make points of light. So, if you were somehow floating there, you would not have seen stars, but you would have been surrounded by a quiet sea waiting to form them. And that waiting is the heart of this story. If you zoom out far enough, the timeline is simple to say without heavy words. First, there is a blinding beginning, whose glow stretches and softens as space expands. Then there is a long pause, when no new lamps have turned on. And then there is a first dawn, when little knots of gas grow heavy enough to ignite. We will save the fireworks for later chapters, and stay in the pause, because it teaches something most people miss, that darkness can be full of preparation, and that important changes often happen where our eyes cannot see them. Like bread rising under a towel or a city quietly building its foundations at night. And the universe too did its slow work in the quiet, letting tiny lumps in the fog pull in more fog so that someday they could become the first neighborhoods of light. This is the journey you are taking now. Not across miles, but across patience. You are learning to stand inside a silence long enough to feel what it holds. How do we know any of this if it is so dark, you might ask? And the answer is gentle and human. We change our tools, because when your eyes cannot help you, you listen. You build instruments that do not chase sparkles, but measure the sky's faintest background. You carry them to quiet places on Earth where human noise is low. You point them upward for long stretches. You remove your own hum from the signal, and little by little a pattern appears. Like hearing a faint chorus after you stop talking. And it says the same thing our best models say, that there was a broad span when space was cool and calm and unlit. When gas drifted, when the first small gatherings grew in the dark like seeds under soil. If you find that disappointing, you are thinking like someone who only loves the fireworks. But if you find it comforting, you are beginning to think like a builder. Because builders know that the time when nothing seems to happen is often when the outline of everything is decided. In this dark interval, the universe is simple in a way that will never return. There are no heavy elements yet, no clouds of smoke from exploding stars, no bright jet from hungry black holes. Only a clean mixture of the lightest stuff and the pull of gravity. And that simplicity is not a flaw. It is a clean page, the quiet classroom where the first lessons will make sense. Because when the first lamps finally turn on, the world becomes messy very quickly. Heat and light change their surroundings, new elements appear, and everything talks to everything else. But here, in the dark, the rules are basic and the flow is calm. That calm matters because it lets little differences grow into big ones. It gives small overdensities time to gather more material. It gives the future lights the mass they will need to ignite. And it gives us a baseline for later. So when we look back, we can say with confidence what changed and when. It might help to hold a picture in your mind, not a diagram, but a feeling. Stand in a large hall before a concert. The stage is set, the instruments are there, the air hums softly. With the building's own breath, you hear people settle in their seats. Then, one more minute passes. A very long minute. And in that minute, no note is played, but everything becomes possible. The audience leans forward, the players grip their bows, the conductor raises a hand, and the silence feels full. That is what the universe's darkest moment is like. A full sill, hence a charged breath, a pause that knows what it is about to become. And if you pay attention to your own life, you have felt this too. The moments before a decision, before a call, before a first step, when nothing outward changes yet. Something inside gathers. The world feels slightly heavier at the edges, because choice is coming, and this cosmic pause is the same, scaled beyond imagination. A long preparation for the first. Someone might be tempted to color this part of the story with mystery for the sake of drama, to say there were secret engines or hidden tricks. But the real story is already beautiful. It says that ordinary rules applied for a long time can build extraordinary results. That gentle pulls over long distances can shape oceans of gas. That patience can structure a universe. Even the word moment is a kindness we use to make the vast feel close. It was not a snap, but a wide valley of time. Yet calling it a moment invites you to stand inside it, as if you could listen to it breathe. And that is enough for our journey today. We do not need to rush forward to the sparks, or rewind into the first flash. Both of those will be visited later. We only need to practice staying here without fidgeting, because staying is a skill, and this is a place that rewards it. The most honest thing to say is this. We learn about this darkness by collecting slight hints, and by asking what else would be true if the story were different. We test ideas. We try to trick our instruments into telling us we are wrong. And when they refuse, we trust what remains, a quiet arc in the sky's background that fits a world where the lights had not yet come on. And the thought that a silence can be measured and dated is one of the tenderest truths in science. It means we can love the quiet with numbers, as well as with awe. Even without the details, you can carry the essence with you, that the universe had a long, deep breath before it spoke in stars. That breath charged the first words with meaning, and that without it the later brightness would not make sense. If what you want is a reason to care, here it is. When you learn to respect a beginning that does not look like a beginning, you train your mind to notice the difference between emptiness and potential, between a blank and a page that is about to be written. You stop judging a room by its lamps, and start asking what might be ready to happen. And that is a powerful habit far beyond astronomy. And if what you want is a feeling to hold at the end of this journey, let it be this soft one. That darkness is not always the enemy of seeing. Sometimes it is the friend that keeps you from being distracted. The clean frame around a future picture. The pause that lets the first note land in a quiet heart. So let the house lights stay down for one more beat. Breathe in the cool air of a universe that has not yet learned how to sparkle. Hear the faint stir of gravity in the wings. And then, without rushing to the next chapter, simply recognize where you are, at the threshold that makes dawn possible, at the most revealing quiet in all of time, the place where everything that will shine is gathering its courage. When you carry that recognition forward, the coming brightness will feel different. Not like noise bursting from nowhere, but like a promise finally kept. And that is the true gift of the darkest moment. It teaches you how to watch for beginnings that arrive without a headline. The cosmic answer to where did we come from? When a child asks, where did I come from? You might point to a family photo or the town on a map. Yet the truer answer is a path that keeps widening every time you take a step. From your parents to your grandparents, from your species to the first animals that crawled from warm seas, from Earth to our star that feeds it, from our star to ancient stars that forged its elements, and finally to a young universe that had not yet learned how to make a single sparkle. And if that sounds too big to hold in your hands, think of it as a set of gentle doors you open, one by one, each door revealing a room that explains the room before it, until you find that your story is not a straight line, but a braid made of family, planet, star, and cosmos woven together so tightly that pulling on any one strand moves the others. Begin with what you can feel, your heartbeat, your breath, your thoughts arriving like birds and leaving like clouds. Then take one step back and notice that your cells are small villages of cooperation built from water and dissolved salts and long chains of carbon that curl and fold into tools. And those chains are made from atoms that follow rules so dependable you could set a clock by them. And those atoms are not local inventions at all, but travelers with long histories, because the oxygen that helps you breathe, the calcium that shapes your bones, the iron that carries oxygen in your blood, and the phosphorus that stores your energy were not made on Earth at all. They were fashioned in stars, long before your planet existed, heated, squeezed, and finally thrown into space when those stars died. And tiny bits of that ash later collected into worlds, one of which became the place you now call home. If you keep stepping back, you find the Our Star at the center of a wide family of planets that began as a cloud of gas and dust, slowly spinning. And as the cloud spun, it flattened into a disk, and inside that disk small grains stuck together like faff, lava turning into dough. Pebbles grew into boulders, boulders into mountain-sized bodies, and the gentle collisions became more serious until one of those bodies swept up enough material to become Earth, while the center of the disk grew so hot and dense that it lit itself and became a star. Our star, and that is why the ingredients of your body match the chemistry of the Our Star outer layers, more than you might expect in a universe of infinite options. Because you and your star were made from the same pantry of dust. Now step back again, and you reach the older stars that came before the Our Star. Stars that acted as factories, turning the very lightest ingredients into heavier ones deep in their cores. And though we will save the technical road map of that process for a later chapter, you can already hold the shape of it in your mind. Stars live by fusing simple things into complex things. And when they can no longer keep that process going, they change or explode. And their endings are the reason your beginning had the right pieces available, which makes every ordinary morning on Earth a quiet inheritance ceremony. Keep stepping and you arrive at an even earlier scene, a universe that began hot and bright, and then stretched and thinned, leaving a faint glow everywhere, as a kind of baby picture, a soft light we can still measure with careful instruments. And though we will explore that glow in depth later, you only need to know this now. It confirms that our story has a real timeline, a before and after, a way for simple to become complex without magic trick. Only patient rules acting over deep time. And that patience is the secret rhythm behind your existence. Somewhere along this path, after the planet cooled enough to keep a stable ocean, and the surface stopped being constantly reset by impacts, chemistry found ways to copy itself, to fold into shapes that helped other shapes, to store hints of what worked so the next round could try it again. Brave chain of improvement is what we call life. Not a sudden leap from nothing to everything, but a staircase, so fine that early steps look like sideways movements until you have climbed far enough to turn around and see how high you are. And from that staircase your own line eventually appears, not as a solitary thread, but as one branch among many on a tree that tried countless forms, most of which ended quietly while a few kept going, and diversified into all the beings you know, and many you have never seen. Perhaps you are wondering how we can be so sure without being there to watch. And the answer is that the world keeps receipts. Rocks hold tiny crystals that cool like stopwatches. Ice traps air from old skies. Riverbeds fossilize footprints and shells. Tree rings widen and narrow with the mood of rain, and even the atoms themselves give off signatures that tell us when they were made, and how long they have been sitting where we found them. And when you line up those receipts, they form a simple arc. Early Earth is hostile, then calmer, then covered in single-celled life that changes the air, then a burst of new body plans, then forests, then creatures that walk onto land, then mammals finding night places, while the dinosaurs dominate the day, then new chances after a great extinction, then the wide, curious primate gaze that eventually wonders about its own origins, which is where you are standing now, asking this question. The most helpful way to hold all this, especially if you are young or new to the subject, is to think in nested homes. Your first home is your body. Your next home is your family. Your next is your species. Your next is Earth. Your next is the solar system. Your next is the Milky Way. And your widest home is the universe itself. And every home builds on the one before, but also depends on the larger ones that hold it. Like a set of bowls where the smallest carries warm soup, but needs the bigger bowls to sit safely. And this nesting is not just a poetic idea, it is a practical way to remember what belongs where. Which pieces of the answer fit in the Earth chapter, and which pieces belong to the earlier chapters of Stars and Space. Now, because this is a question about origin, it is easy to slip into either grand claims or small myths. So let us put down 5 clear, human-sized anchors. First, you come from other living things, which passed you a recipe, written in a simple alphabet, carried by a long molecule, and the alphabet lets your body build and repair itself, and also keeps a memory of your deep family. Second, those recipes are written using elements your planet collected long before there were people, and those elements were made in stars. Third, your planet is one result among many in a process that turns rotating clouds into star systems, which means that what happened here is a kind of common behavior of matter under gravity, rather than a one-off tree. CK fourth. The whole setting in which clouds form and stars light up is given by a universe that began hot and then expanded and cooled, leaving clues in the sky we can measure. Fifth. Nothing in that chain requires you to stop feeling wonder. In fact, the more clearly you see each step, the more the whole thing glows with meaning, because it works without special pleading. It is a story that invites your trust because it repeats the same habits at different scales. Slight differences add up. Steady rules under pressure give astonishing results. And time is a partner, not an enemy. Notice what this answer is not doing. It is not blaming your existence on chance alone as if you fell out of a hat. Nor is it shutting the door with a single line. It is describing a path that includes both openings and constraints. There were many possible worlds around the young our star, but a small subset had the right size and position and history to hold liquid water on the surface. For long stretches, there were many possible branches on the tree of life, but some had the combinations that handled change well, not as the inevitable goal of the universe, but as a natural outcome of its rules playing for a long time on a generous stage. If you want an image to tuck into your pocket, picture a long beach at low tide, smooth, wet, almost featureless at first glance. Then let a breeze blow for an hour and watch ripples appear in the sand. Then larger patterns, and if the wind keeps blowing, and little streams trickle from the dunes, you get channels and islands and tiny deltas. And none of it was planned, yet none of it is random scribble either. It is the result of simple pushes repeated patiently. And if you walked across that beach and found a small shell imagining itself separate from the wind and the water, You would smile and tell it a secret. You belong to the whole scene. And that is the feeling this answer offers. Belonging without shrinking the mystery. Because this is meant for all ages, let us keep two friendly rules in mind. Whenever the story feels too big, come back to something you can touch, like a rock on your windowsill or a glass of water. Both are pieces of ancient journeys, and whenever the story feels too small, step back to a bigger bowl. Your neighborhood becomes your planet. Your planet becomes your star's family. That family becomes a swirl inside a galaxy. That galaxy becomes one island among many. And suddenly you have room to breathe again. Because origins are easier to handle when you can zoom. There is a quiet responsibility that comes with knowing where you come from. If your materials were made in the hearts of stars, and your life was shaped by a planet that kept you safe for billions of years, then caring for your small corner of that planet is not a chore, but a way of honoring the older work that made you possible. And if your mind is the part of the universe that can ask about the universe, then using it with care, patience, and kindness is how you complete the circle. You are not here only to consume the story, but to understand it enough to make good choices inside it. And when you reach the end of this answer, do not rush to fix it to a single sentence. Let it remain a living map, a path you can walk again from different starting points. Sometimes from Earth outward, sometimes from the early universe inward, sometimes from your own breath, all the way back to the first calm seas. Because different days need different doorways. And the more doorways you know, the less likely you are to mistake a hallway for a home. So the cosmic answer to where did we come from is that you come from a long patience that began before there were eyes to admire it. From a sequence that turns simple into complex without cheating. From clouds that became stars. Stars that enriched space. Dust that became worlds. Worlds that hosted chemistry. Chemistry that learned to remember and copy. Copying that tried and failed and tried again until one day you looked up and asked, and if you listen closely you can hear the whole chain answer back with a single feeling. Welcome. You belong here. Not by accident alone and not by design alone, but by a steady unfolding that makes room for you. And if that leaves you both calm and curious, that is perfect. Because the next steps of the series will open the doors we passed lightly today and show you their rooms in detail. And you will see that learning the larger story does not push you away from yourself. It brings you home. The story of Stardust, humanity's connection to the cosmos. If you want to feel where you belong in the universe, don't look up for a grand answer. Look down at your own hands and imagine the journey of the atoms inside them. Because the simplest truth with the deepest warmth is this. The substance of you was forged elsewhere and long ago, in places that burned and places that broke. And it traveled, cooled, clumped, sailed through darkness, and finally came to rest in a world where it could become breath, heartbeat, memory. That is the story of Stardust. And it is not a metaphor meant to make you smile. It is a plain description of how the pieces of you came to be. And once you trace even one ingredient back to its source, you begin to see a chain of events that links your breakfast spoon, the salt on your skin, and the thoughts you are having now to the wider, older theater of the cosmos. Start with something familiar. Iron in your blood gives each cell the strength to carry oxygen. Calcium in your bones lets you stand and reach. Carbon shapes the flexible tools called proteins that build and repair you. Oxygen partners with hydrogen to make the water that fills most of your cells. And phosphorus stores energy, so your muscles can move and your mind can think. None of those elements were manufactured on Earth like products in a factory. Earth collected them. But they were made before Earth existed by stars that lived, worked, and in many cases died. Because a star is more than a light in the sky. It is a real oven where simple matter is pressed and heated until new kinds of matter appear. And when those stars change or explode, the new matter is thrown into space as tiny grains, rocky bits, and gas clouds that drift and gather again, beginning the long loop that eventually makes planets, and much later, people. You do not need a textbook to picture this loop. Only a few mental images in calm old stars. Gentle winds puff outward like slow breath from a sleeping giant, and carry with them fine soot, grains of carbon, silicates, and other minerals, that cool and harden into dust, in violent endings. A star's outer layers blast away in a bright storm, and as the hot cloud spreads and cools, it condenses, like steam turning to frost on a window, into countless tiny solids that will spend millions of years traveling. Some of these grains are the size of smoke particles. Some are closer to the size of sand. All are small enough to drift with gas through the wide spaces between stars. And because the universe is patient, these tiny travelers have time to be changed by light, by mild shocks, by faint magnetic fields, and by dancing together in dense patches where everything is gently slowed. That drifting dust is not dead powder. It is a surface where chemistry can practice, a kind of cosmic workbench. Hydrogen atoms that would otherwise bounce past each other can meet and stick on dust, making the simplest and most important molecule molecular hydrogen. Oxygen can join with hydrogen to make water on those same surfaces. Carbon-bearing gases can settle and form more complicated species. In cold clouds, coats of ice can form around grains like sugar crusts, storing little libraries of simple molecules that will matter later over time. Gravity squeezes parts of those clouds tighter, and in the middle of each squeeze, a new star will light up, surrounded by a flat disk of gas and dust. And inside that disk, grains bump and join and grow, from specks to pebbles, to boulders to worldlets, until a few become planets. This is not a myth, but a behavior. The way flour and water become dough if you keep kneading. And our solar system carries the fingerprints of that process in every meteorite that falls, and every small ring of dust we still see shining faintly in the night sky as a soft band called zodiacal light. If you want something you can hold that is older than our star, science has actually placed such pieces on a lab table. Inside certain meteorites are tiny crystals and grains with strange isotopic accents that do not match anything made in our own solar system, which tells us they were formed in other stars before our star was born and somehow survived the violent mixing that built our planets. When researchers dissolve the meteorite rock and isolate those grains, bits of silicon carbide, graphite, even nanodiamonds, they measure their atomic dialects and can tell whether they came from a calm, puffing star or from an explosive event. In this way, we do not just say, we are stardust. We read the dust like a travel journal and learn what kind of star wrote each chapter. For the very heaviest ingredients in your life, gold in a wedding band, iodine in a salt shaker, the platinum in electronics, the story adds a dramatic page. Some elements need not just heat, but a flood of free particles to form. And nature provides that in rare, intense events. For a long time, many suspected that some exploding stars could do it. And more recently, we have seen two dead stars made of pure neutrons collide and pour out a bright, unusual glow that tells us new heavy elements are being forged in the briefest storm you can imagine. When you look at something made of gold, you are touching matter assembled in a flash of violence between objects smaller than a city, yet heavier than a star, a gesture from a distant calamity, now quiet on your finger. But stardust is not just about jewelry and lab samples. It is about your daily life in plain view. The salt on your tongue, the lime in your tap water, the rust that creeps into a garden tool, the oxygen you draw into your lungs. Each is a chapter of stellar work written into ordinary moments. What changes you is seeing that ordinary is a word we use when we forget to widen our view, because the table you rest your elbows on is pressed. Together stardust. The screen you read from is refined stardust. The blood moving through your palms carries the output of ancient forges, and even the thoughts you are having are electrical patterns in a brain built from material that once sailed between our stars. The connection becomes practical when you realize dust is not just heritage but helper. In newborn star systems, the presence of dust determines how quickly a disk cools, how well the raw material can clump, which minerals form first, and even which paths are open for making simple precursors to life. Small bodies like asteroids and comets carry dust inward to young planets, sprinkling them with water and carbon compounds. On early Earth, countless microscopic grains fell through the air and water like soft rain, delivering both minerals and the tiny rough surfaces on which early molecules could assemble into longer, more useful chains. And even today, roughly 100 tons of fresh space dust fall on Earth every day, silent and golden before dawn, feeding the upper atmosphere with bits of metal that seed faint noctilucent clouds, and, as they settle, become part of our soil and oceans. You walk on a thin blend of planetary rock and new gifts from space without noticing. Because the stream is gentle and the scale of your life is small compared to the skies. Some people worry that calling us Stardust makes us small, but the opposite is truer. It makes you continuous with the largest things you can imagine, without taking away your personhood. You are not reduced. You are extended. Your body is a temporary island, where very old atoms cooperate for a while before returning to the wider sea, and there is comfort in that, because it means belonging is not something you earn by achievement. It is built into the material you are made from. At the same time, there is responsibility in it, because the same dust that built you is still cycling through space and through your planet. And how gently we treat our corner of the cycle determines what shapes it can take next. When you recycle the metals in an old device, when you keep water clean, when you plant a tree, you are helping the dust keep its options open. You might ask, how do we know this story is not just a nice idea? And the answer rests on many kinds of simple evidence that fit together like puzzle pieces. We can split starlight and read the dark lines and bright bands that reveal which elements are present in hot gases far away. We can watch the fingerprints change as stars age, telling us new elements are being made inside. We can see supernova remnants glowing in colors that match freshly minted material. We can detect dust around aging stars and young disks, directly in infrared light. We can catch the faint afterglow of rare collisions that build heavy elements. And we can hold in our hands meteorites that carry tiny, stubborn grains, whose inner ratios of atoms look nothing like anything formed near our star. Any one clue would be interesting. All of them together make a calm case you can trust without stretching. If you keep your language simple, the heart of the story is easy to remember. Stars cook, stars shed, space stores, gravity gathers, disks build, planets form, comets deliver, oceans and air welcome, life learns, and awareness asks. Your connection to the cosmos is not a thin thread, but a woven fabric of repeated behaviors that turn simple beginnings into rich outcomes. And you sit at the point in that fabric where it looks back at itself and says, I see the pattern. Stand for a moment in that feeling. The ring on a hand, the hemoglobin in a vein, the salt on the lip, the whisper of dust arriving in the night. They are all proof that the universe does not just surround you, it continues through you. And let that thought soften the way you move through your day. Because once you know you are built of traveling history, it becomes easier to be patient with yourself and kinder to the world carrying you. And if this makes you curious about the very first chapters, before there were any stars to cook with, before there was dust to store anything, then you are ready for the next door, because to understand how the first ingredients were set on the table at all, we will have to step backward in time to the earliest seconds when the universe learned to make the simplest building blocks that Stardust would later refine. The first seconds after the Big Bang. You might expect the universe's first seconds to be a noisy fireworks show. But the truth is quieter and stranger. They were a fast-cooling kitchen where ingredients kept appearing and vanishing so quickly that survival depended on timing. And the whole recipe was guided by only a few simple rules, repeated at incredible speed as space itself expanded. We cannot yet speak with confidence about an absolute first instant, because our best equations fall silent at an edge we have not crossed. But immediately after that edge, the universe was already hot, dense, and racing outward. And the way to understand what followed is to picture a soup so energetic that familiar things could not exist. No atoms, no molecules, not even the protons and neutrons that later build them. Only the smallest building blocks swirling in a bright crowd, colliding and converting into light and back again. while gravity tugged on everything evenly and time was counted. Not by clocks on walls, but by what could survive the heat from one heartbeat to the next. One of the first helpful ideas in this story is that very early on, the fabric of space may have expanded extremely quickly for a brief moment, smoothing out bumps and stretching tiny quantum jitters into gentle ripples, like a sheet being pulled tight. And although the exact details are still being tested, those ripples are useful, because they became the faint pattern that later told matter where to gather. Yet, for our purposes here, the important part is what the heat allowed and what it denied, because temperature was a referee more decisive than any person could ever be. At the highest temperatures, energy and matter were two ways of describing the same crowded dance. Particles and their mirror partners popped out of light and disappeared back into it in a steady exchange, and the forces of nature behaved differently than they do today, because the environment treated differences as if they were not there, a bit like ice and water being indistinguishable in a pot that is violently boiling as expansion cooled the soup ever so slightly. Distinctions emerged. The known forces began to act like themselves, and the smallest building blocks called quarks started to prefer company, locking together in threes to form protons and neutrons when the furnace dipped below a certain point, a bit like marbles that suddenly stick when the glue finally sets. This sticking did not happen all at once, or in peace. It happened in a roaring crowd where collisions were still common, and the air, if we can call it that, in that crowd, every particle had a partner with opposite charge, and most of the time the crowd behaved fairly. Matter met antimatter, and the pair vanished into light. Then light made a new pair somewhere else, over and over in a blur. Yet, for reasons we are still exploring, just enough extra matter over antimatter that when the last big cancellations finished, a small surplus of ordinary matter remained. And small here does not mean unimportant. It means about a grain of sand left behind for every beach of light. But that grain of sand was the seed of everything later, including you, if the balance had been perfect. Both sides would have erased each other completely, and the universe would have cooled into a lonely bath of light, with no atoms, no stars, no questions asked or answered. So one of the quiet wonders of the first seconds is that this delicate surplus existed at all. As the temperature fell further, the protons and neutrons, those new sturdier ingredients, still shifted back and forth through interactions with lighter particles. But that back and forth slowed, and then effectively froze, when the soup thinned and cooled to a level where such rapid swaps were no longer favored, and the ratio that resulted meant more protons than neutrons would be left available for later chemistry. A detail that sounds small but sets the stage for how much helium and hydrogen the young universe would carry, which is the topic for another chapter. At nearly the same time, another important group made its quiet exit. Neutrinos, almost ghostly in how little they interact, were so common in the first seconds that they helped set the pace of cooling, and then, as the density dropped, they drifted free, leaving behind a sea of neutrinos, still crossing space today, hard for us to catch but part of the universe's memory of that time. Then came a sweeping change in the crowd of light particles and their partners. The background was still hot enough to fill space with electrons and their opposites in large numbers, created and destroyed in pairs, until the temperature fell to the point that it was easier for those pairs to disappear into light than to be created again from it. And when that happened, the number of free electrons dropped sharply, but did not go to zero. Enough remained to make the young plasma a place where light could not travel straight, bouncing repeatedly from charged particles, the way a beam of light scatters in a cloud, which is why the universe stayed opaque for a long time after, with long measured on cosmic scales. In this bright fog, the expansion continued, every second stretching space and cooling the soup, and with each small drop in temperature, certain reactions slowed. Certain ingredients survived a little longer, and the overall identity of the cosmos shifted from too hot for structures to ready soon for simple ones. Even though soon still meant minutes, not years. To keep this accessible, imagine a kitchen where you are making candy. The syrup is so hot at first that nothing you add can hold its shape. Then, as you lower the heat, there is a narrow window when stirring matters most. If you stop too early, the mixture burns. If you wait too long, it hardens before you can pour it. And in between, there is a sweet moment when it can be shaped. The first seconds were like finding and passing through that window at unimaginable speed, with the laws of physics playing the role of an expert chef, who does not guess but simply follows the properties of the ingredients. And nothing in this picture requires secret tricks. Just the clarity that comes from understanding how heat, density, and time cooperate. We do not need to lean on heavy formulas here to appreciate the story. It is enough to know that the cooling rhythm determined which parts of the crowd could last long enough to matter later. You might wonder how we can talk about this time with any confidence if we were not there to see it. And the answer is pleasantly down to earth. Our laboratories can recreate tiny pieces of the early conditions by smashing particles together and heating small volumes to incredible energies for brief moments. And what we observe in those experiments matches the expectation that at high temperatures cakes roam free, and at slightly lower ones they prefer to be bound. Just as the story requires. We also read the first seconds through the consequences they left behind, not by direct snapshots, but by the numbers that later processes had to inherit. And those numbers show up in the abundance of the lightest elements, in the faint patterns imprinted on the sky as the universe did further, and in the very existence of structure, all of which we will explore later with appropriate care. It is important to be honest about what is settled and what is open. The general outline of fast expansion, hot soup, cooling, binding, and slight matter surplus is strongly supported, while the exact mechanism that created the tilt between matter and antimatter is an active area of work, and the precise nature of the very earliest expansion remains under study. But you do not need all the technical pieces to grasp the meaning. The early seconds were a race in which the rules were simple and the stakes were everything. In this race, gravity had an unusual role, because while it would one day help gather gas into stars, at the beginning, it acted mostly as a pressure that the soup pushed against. And as space expanded, the push weakened, easing the way for new structures to appear. Yet, even then, tiny differences in density. Those gentle ripples stretched from earlier fluctuations were present, so faint you could not have seen them if you were there, but real enough to make some places just a touch denser than others, which over enormous stretches of time would give those places a head start in collecting material. And later, much later, become the sites where galaxies would grow. This is the part where the mind enjoys holding two scales at once, seconds that write rules for billions of years, and a soup so uniform that a difference of one part in 100,000 is enough to direct the future. If we pause and look inward for a lesson, the first seconds teach humility and courage at the same time. Humility because the universe did not need elaborate instructions to get started, only steady laws and patience. And courage because the smallest asymmetry, a tiny preference for matter, a delicate ratio freezing before all swas could finish, changes everything downstream, reminding you that what seems minor can be decisive when the stage is large and the timing is tight. They also remind you that not all beginnings look like the beginnings we are used to in stories. There was no drum roll, no audience, just a set of conditions flowing into new conditions under their own logic, and from that flow came the first durable pieces that later chapters will shape. To close this gentle tour, gather the thread without pulling it too tight. In the first seconds, the universe cooled from unbearable to merely extreme. Quarks stitched themselves into protons and neutrons. A slight excess of matter survived its mirror, ghost-like neutrinos slipped away into a background that still crosses us. Light kept the young plasma foggy, while electrons and their partners vanished in pairs. And the key ratios that decide how much of each simple ingredient would soon form were set by the pace of this cooling. We will not mix in the details of the next step here, because that belongs to its own doorway, but you can carry this feeling into it, that the first seconds were about making sturdy pieces and setting proportions, and the next minutes will be about using those pieces to make the universe's first stable elements in a calm that follows the sprint. The birth of the first elements, hydrogen and helium. There is a moment in every language when shapes become letters and letters begin to spell the first words. For the universe, those letters were hydrogen and helium, and they were written not with ink but with time and temperature. As a few minutes after the beginning, the roaring heat eased just enough for the lightest building blocks to lock together and stay, turning a bright, formless crowd into a simple, lasting alphabet from which everything else could eventually be composed, to see it without getting lost in jargon. Picture the scene like this. First came a furious 2. Hot stage where any attempt to stick was instantly undone. Then, a brief grace period as space expanded and cooled. The glue started to hold, and in that window, the cosmos made almost all the hydrogen and helium it will ever have, quickly, quietly, and with results so consistent that we still measure the same proportions today, in ancient, untouched gas. What actually changed at that turning point is easy to say in everyday terms: protons and neutrons. The tiny beads that would one day sit at the hearts of atoms finally found a way to clasp and not be torn apart by harsh light. And the first clasp had a name: deuterium, a simple pair of one proton and one neutron that acted like a latch. Yet earlier the universe was so hot that every newborn latch snapped immediately, like frost melting on a warm plate, so nothing else could be built. Only when the background calmed a little did deuterium survive long enough for a cascade to take off, latch linking to latch until 4 beads sat together as a snug square we call helium-4, a nucleus so tightly bound that almost every neutron within reach ended up inside one, leaving the rest of the protons free as hydrogen. The whole production run took mere minutes, not centuries, because once the latch could hold, the reactions went as fast as the thinning crowd allowed. And then, just as quickly, the show ended when the mix became too diffuse and too cool for further assembly, like batter poured thin enough that the last drops never meet, freezing the result into a universe dominated by hydrogen with a generous quarter by mass of helium, and the faintest trace of deuterium, helium-3, and a whisper of lithium to mark that it really happened. If the numbers help anchor the picture, hold these 2 in your pocket without worrying about the decimals. By mass, the young cosmos left the kitchen about 3 parts hydrogen to 1 part helium. By count of particles, it was far more lopsided, roughly 12 hydrogen nuclei for every helium nucleus. Because helium is Va, that simple mix is the reason later stars could ignite and live as they do. But we will save the star story for its own room and stay with the quiet brilliance of these first minutes, because there's a deeper lesson in how they worked. Nothing complicated was required, only the right order: first survive as deuterium, then climb to helium, and the right timing stop when expansion makes further climbing unlikely. And from those 2 plain rules came a stable foundation for everything still to come. You might gently ask how we can speak so confidently about a time no one could watch. And the answer is as down to earth as a kitchen scale, and as skywide as a map. The universe left 3 kinds of notes about what it did. What's in old pristine clouds, which still show the same deuterium to hydrogen ratio you'd expect from this brief factor. What we make in tiny controlled collisions on Earth, where matter at high energies behaves just the way this story needs it to, and what we read in the later glow of the sky, whose patterns depend on how much ordinary matter existed, and in what mix these independent notes harmonize, giving a calm yes, without our needing to chase exotic fixes or strained coincidences. And that agreement between simple theory and varied measurement is part of why this chapter of the origin story is one of the most trusted. It helps too to keep what was made and what could be seen separate in your mind. The nuclei of hydrogen and helium were born in these minutes, but atoms with quiet electrons would not appear until much later, when the universe had cooled enough for electrons to settle into orbits without being knocked free again. Until that later calm, light still bounced around in a bright fog, unable to travel in a straight line for long. Which is why this minute-old chemistry, though decisive, did not yet make a visible sky. Think of it like words forming on a page, long before the page is handed to the reader. The meaning is there, but the reading must wait for the ink to dry. There's beauty in how little you need to memorize to carry this with you. Step 1. The furnace eases and deuterium. The first latch starts to survive. Step 2. Latches join into helium-4, soaking up nearly all the neutrons. Step 3. The crowd thins and the reactions wind down, leaving a universe rich in hydrogen with a steady share of helium and tiny markers in deuterium and lithium that serve as the cosmos's signature. That's it, really. And from that spare list, you can already guess consequences without peeking ahead. Hydrogen's abundance means stars will have a long, flexible fuel. Helium's presence shapes how those stars breathe. The traces of deuterium act like a thermostat reading. We can check billions of years later to see that the furnace once sat at the right setting. If you want one image rather than 3 steps, swap the usual fireworks for a calmer craft. Imagine a potter at a wheel with a brief moment when clay consistency is perfect. Too wet and the walls collapse. Too dry and nothing joins. Then picture deft hands raising a simple bowl in one practiced sweep. The early universe behaved like that potter, not because it decided to, but because its materials and weather fell through a special range. And once the bowl was lifted, nothing in that session could make it taller. Time to let it dry and use it later. That bowl is the hydrogen-helium mix. Simple and sufficient, waiting silently while the rest of the workshop gets ready. Perhaps the most human thing to notice in this chapter is how much depends on patience and restraint. The cosmos did not rush to make heavy elements. The fancy tableware will come much later inside stars. If you hold that pattern up to your own life, it has a gentle wisdom. Do the simple first thing cleanly. Accept the pause. Trust that later complexity will have its turn. The universe did, and you are here to ask about it. When you set this paragraph down, you don't need to keep the exact temperatures or times. Only the rhythm, an overheated world cooled to a sweet spot. The lightest pieces linked into lasting pairs and quartets. The mixture froze into place as space stretched, and the result, abundant hydrogen, steady helium, tiny traces, became the durable background of matter from which stars, planets, oceans, and eventually questions could arise. And if you're curious about what happens when those long-trapped rays of light finally slip free and turn the whole sky into a soft photograph of its own past, keep that curiosity warm. We'll walk into that light in the very next room, the birth of the cosmic microwave background. There was a day when the universe became transparent, not with a switch, but with a slow, cooling breath. And if you could have stood anywhere, then you would have seen something simple and astonishing. Light that had been trapped for nearly 400,000 years, finally slipping free and heading out in straight lines, beginning a journey it is still on today as a soft glow that comes to us from every direction. Before that day, the cosmos was a hot, bright fog, a crowded mix of tiny charged particles, and light where every step a photon tried to take ended in a bump. A scatter, a change of course, the way headlights turned to haze inside a thick cloud. But as space expanded, it cooled to a point where those free electrons could finally settle down into atoms, mostly hydrogen. And when that happened, the fog thinned in an instant of cosmic time, and the light decoupled from matter, which is a neat way of saying it could finally travel without being constantly knocked around. And the universe took what amounts to its first clear photograph of itself. That picture is what we call the cosmic microwave background. Microwave, because the light has been stretched by expansion from a warm, reddish glow down to very long, very gentle wavelengths we pick up with antennas, rather than eyes, and background because it is everywhere, filling the sky like the faintest wallpaper, not bright enough to notice with your senses, but perfectly measurable with simple instruments, which is how a pair of engineers once mistook it for persistent static, and then helped prove it was a relic of the beginning. To hold this moment without getting lost in numbers. Imagine a nursery finally quieting after a long cry, not because anything dramatic explodes, but because the conditions change just enough for calm to appear. The temperature has dropped to the kind of heat your oven uses. Electrons have taken their places around nuclei, and the light that was rattling around inside the room can go out the door. And since there are no stars yet, that just, freed glow becomes the only light in town, streaming through a universe that has turned from opaque to clear in a single chapter. What makes this light precious is not only that it is old, but that it is slightly uneven in exactly the right way, smooth to 1 part in 100,000, peppered with tiny warm and cool patches that are the fingerprints of the earliest ripples in the cosmic soup. And those faint mottles, barely more than a whisper in the data, are the seeds from which every later structure grew, because places that started out a hair denser than average slowly gathered more matter, while places that started a hair emptier gave some up. And over great spans of time, those slight preferences bloomed into galaxies, clusters, and the webby pattern we map with telescopes. Now, even the pattern of those patches carries a story you can tell in plain language. It looks like frozen music, the after effect of sound waves that once rang through the hot plasma before the fog cleared, compressing and rarefying the gas the way a drumhead shivers. And when the universe became transparent, the song stopped and the positions of the notes were left imprinted on the light. So when we make a full sky map of the background glow and study the sizes of the hot and cool spots, we are reading a kind of cosmic score that tells us how big the universe was then, how fast it was expanding, how much ordinary matter it contained, and how much additional mass was present that we cannot see directly. You do not need to memorize the values to appreciate the point, which is that this single quiet photograph lets us weigh and measure the cosmos when it was a baby with surprising precision, and the answers agree beautifully with what we infer from completely different evidence later on. The kind of cross-check that gives science its backbone. There is another layer of information in this light that is easy to picture, even if the word sounds technical: polarization, a preferred orientation of the light's tiny electric wiggles set by the last scatterings of free electrons just before the fog cleared, and by mapping that subtle orientation across the sky, we gain a second angle on the same early sound waves, and on later processes as well. A bit like learning to read not only the brightness in a photograph, but the direction of shadows to tell what time the picture was taken. Collectively, these measurements turn the background from a curious hiss into a detailed portrait. First with balloon experiments, then with satellites that blurred the universe's face, less and less, until we could see the freckles. And with every improvement, the broad picture stayed the same, while the details sharpened. A strong sign that we are not fooling ourselves. Perhaps the most human way to feel the importance of this moment is to think of it as the universe's first chance to be seen as it truly was. Then, not through a distorting fog, but directly, and that chance was brief and decisive, after which the light simply kept going, cooling in color with the expansion. Until today, it matches a temperature just a few degrees above absolute zero, an invisible blanket, so even that engineers have to subtract it from sensitive instruments, and yet so informative that it anchors our entire timeline. Notice too, what it does not show: there are no stars in that picture, no galaxies, no bright points at all, only the first hints of where such things will later gather, which is why this chapter naturally hands off to a long, starless night when gravity quietly goes to work, pulling on those tiny imbalances until the first lights can be born. If you want a single sentence to carry forward, let it be this: the birth of the cosmic microwave background is the moment the early glow of the universe escaped the fog, carrying with it a crisp, faint memory of everything that had happened so far and a map of what would happen next. And because that glow still bathes us, we can read the memory and the map today, turning an ancient clearing of the sky into the most reliable guide to our origins we have. And from that clear beginning, the story continues into darkness again. A necessary night where no lamps yet burn, and the small seeds left in this light begin very slowly to grow. The Dark Ages, millions of years without light. Imagine stepping outside, night after night, and discovering that dawn never arrives. Not tomorrow, not next month, not for a very long stretch of cosmic time, and yet the darkness isn't empty or still. It is busy underneath, like a city whose lights are off, while roads, bridges, and foundations are being poured in the dark, and this is the best way to feel the era we call the Dark Ages of the universe. The long interval after the first light of the early glow has slipped free. But before the first stars have learned how to shine, the fog has cleared, space is transparent, the sky is open in every direction, and still there are no new lamps, just a thin, neutral gas spread almost everywhere, quietly cooling as the universe expands, with gravity taking over as the main storyteller, leaning on tiny, inherited ripples and coaxing matter to drift, gather, and very slowly choose where the future's islands of light will be built. In this starless night, the universe practices patience, the gentle bumps in density, so faint they would be invisible to your eye. Give some regions the slightest head start, and gravity uses that advantage like compound interest, pulling in more gas where there is already a little extra, and leaving other regions a little poorer. Over millions of years, this unevenness, repeated and repeated, sketches a web across space, a pattern of filaments and knots and wide, quiet voids in between. And you can picture that web without equations. If you think of rainwater on a window, how it threads together along the faintest grooves and gathers into beads. At the crossings, dark matter, invisible but abundant, is the scaffolding of that web, laying out the large-scale structure like rebar in concrete, and ordinary gas drapes over it, feeling its pull and sliding along its lanes toward the intersections, where future galaxies will one day grow. Nothing flashes here, nothing blazes, but everything important about tomorrow's map is being decided now. The gas itself is changing in a straightforward way that even a child can hold. As space stretches, the gas cools. Not because something turns the thermostat down, but because expansion gives each particle more room and less energy to share. And without the scalding background that used to knock electrons loose, atoms keep their partners and drift in peace. At first, this lonely gas stays warm compared to the whispering light that fills the universe. But later the balance flips and the gas becomes colder than the glow around it. A quiet inversion that matters because cold gas is easier to gather and easier to compress. And when gas compresses, it heats again a little, making pockets of warm breath in a cold room, small hints that the simple cycle of cool, fall, warm, and cool again, nature's basic rhythm, has begun. These pockets are not stars, not yet, but they are the first rooms where a spark will one day be possible. If you want to know what kind of weather a starless universe has, it is the weather of slow rivers and headwinds. Gas does not fall straight down into the waiting arms of dark matter. It meets a breeze left over from the earlier era, a gentle drift between ordinary matter and the dark skeleton that carries it, so that in some neighborhoods, the gas lags behind the scaffolding like leaves caught in a current, and in others, it catches up more easily. This quiet headwind doesn't stop the gathering, but it delays and redistributes it, making the coming dawn patchy by design. Some places will light up first, others will take their time. And this is why the universe does not turn on like a ceiling lamp, but brightens the way a town wakes before our star eyes, porch by porch, street by street. Something else subtle is happening in the dark. The first tiny amounts of the simplest molecules slowly assemble in the gas, not the complex chemistry of life. Those chapters are far away, but modest, helpful bonds that let gas shed a bit of heat more efficiently when it is squeezed. Since there are no stars yet, there is no harsh starlight to break these fragile partners, so they can accumulate in peace, giving future clouds a way to cool and settle when gravity presses them. You can think of them as the universe's early radiators, small but crucial, because cooling is the permission slip required for gas to collapse. Without it, the gas would heat, push back, and stall with it. The gas can continue inward and make denser hearts where later physics can take the lead. On scales much larger than clouds, the web keeps tightening. Filaments feed the knots like highways delivering supplies to growing towns. And as material arrives, the invisible halos at the crossings grow more massive. With mass comes a deeper gravitational well and a warmer welcome. in falling gas shocks and warms as it arrives, then tries to cool and settle. So each knot becomes a busy construction site with two simple competing processes: gravity saying, "Come in, come closer," and pressure saying, "Not so fast." And the outcome of that conversation decides which places will be ready to ignite first. Keep the picture human-sized, and the idea is friendly. You cannot light a campfire with logs alone. You need kindling, and patience, and the right dryness. And the dark ages are the long evening, when kindling is being gathered and dried under a clear, moonless sky, because there is no new light. The only glow is the ancient afterlight stretched thin across space. And that makes this era sound lonely, but there is a deep comfort to it. The universe is manageable here, simple in composition and rule, free from the noisy feedback of stars exploding and black holes roaring. It is a clean laboratory where gravity has the floor and gas follows. And that simplicity is why this period is precious to science. If we can read it well, we can test our basic understanding of how structure grows from almost nothing to something. And the way to read it is to pay attention to the patterns it leaves in the faintest kinds of light, and in the arrangement of matter we see later. A detective's job in a quiet neighborhood that once solved makes every later clue easier to trust. What you should not do is mistake dark for inactive or boring, the way we sometimes do in our own lives when nothing dramatic is happening. The dark ages are the training montage, with the sound turned down, halos assemble, filaments lengthen. The first modest molecules practice their cooling. Small flows learn to feed larger ones. The headwind carves differences between neighborhoods, and the cosmic web, still soft, settles into a firmer outline. By the time the first lights arrive, the stage directions are already written, and the actors have marks on the floor. They will follow the web, not ignore it. So the shape of tomorrow's galaxies is a respectful reply to the lines drawn tonight. If you need a single image to carry forward, picture a vast plain at winter dusk. No lamps, no fires, only a slow movement of snow into drifts along invisible fences. Come back after many nights, and the ridges will be high, and the valleys clean, and if you look closely, you will see delicate crystals gluing the drifts together, so that a small spark might one day catch in the sheltered hollows. This is the dark ages, drifting, piling, shaping, crystal by crystal, wind by wind, millions of years with no our star eyes, and yet every detail of the coming morning prepared with care. It is tempting to skip ahead to the first stars, but there is value in ending here and letting the quiet sink in, because understanding this long lampless interval changes how you see the rest of the story. The first glow after the beginning was not the same as starlight and could not make structure by itself. Real structure took time, and that time was spent mostly in darkness, with gravity's patient hand setting the table. When you feel restless about slow progress, in science, in your work, in life, remember that the universe itself took millions of years of night to arrange the furniture before turning on even a single lamp. And it did not waste a minute of that night. So hold this room in your mind exactly as it is, silent, starless, full of motion, and let it hand you gently to the next door, where the first truly new lights will appear at last. Not as an explosion everywhere at once, but as a handful of fragile fires kindled at the deepest crossings of the web. Proof that the darkness did not mean absence, only preparation. Characteristics of population 3 stars. Picture the first campfire in a world that has never known flame, not a bigger version of later fires, but a different kind of fire altogether, made from simpler wood and burning in a new way. That is the spirit of population 3 stars, the earliest generation to ignite. After the long starless night, and to recognize them, you do not look for fancy ingredient, but for the lack of them. Because these pioneers formed from pristine gas that contained almost nothing except hydrogen and helium, with a trace of the lightest seasoning, no carbon dust to help cool, no oxygen or iron to mark their breath, no metals of any kind by the astronomer's broad definition, and that elementary recipe shaped everything about their character, from how they came together to how they shone. Imagine trying to bake bread with flour and water only. No yeast, no sugar, no oil. The dough behaves differently. It warms and cools at a different pace. It forms larger, simpler loaves. And in the early universe, the gas did something similar, without heavier elements to radiate heat away efficiently, or to form dust grains that help clumps shed warmth. Clouds could not fragment into many small seeds as easily, so the places that did manage to compress tended toward bigger central lumps that were ready to light once they were heavy enough. And the stars that resulted were not merely big, in a casual sense. They were shaped by a physics of simplicity that favored scale. Their surfaces ran blisteringly hot, and their color skewed toward blue, white pouring out hard ultraviolet light that cut through the quiet gas around them. A harsh daybreak after a very long dusk, and their spectra, the fingerprints of starlight, would have looked strikingly plain compared to later generations, lacking the forest of lines that heavier elements carve, like a clear voice singing a single pure vowel without the consonants we are used to hearing. Because they began with no heavy elements, even their internal engines had to improvise in the earliest moments, starting hydrogen burning in the basic way, and only later, as a little carbon could be made in the core, moving into the faster pathways that require those catalysts. And while you do not need the technical names to appreciate this, it is enough to sense how firstness penetrated every layer of their being, from the light they gave off to the way the light was produced. Their homes were not grand cities, but small, dark neighborhoods, humble halos in the cosmic web places, where gravity's patient tug had drawn in enough gas for a spark, and around each newborn star, the darkness took a step back, not everywhere at once, but in growing bubbles of influence, the surrounding hide. Rogan felt their light and changed state. The thin medium warmed and thinned, and the invisible lanes of the web began to glow at their deepest crossings. Yet even as they altered their surroundings, these stars remained products of their environment's simplicity. And that shows up in details you can hold in plain language, with no heavy elements to grab the star's light and push material outward. The usual line-driven winds that strip mass from later hot stars would have been weaker. So much of the star's life was a contest between its own pressure and its immense weight, without the steady peeling that metals enable. And that difference in how they hold themselves together likely shaped both their brightness and their endings. You will explore how bright and how long in the next rooms, so keep those doors closed for now and concentrate instead on the traits that make them themselves. Pure beginnings, fierce color, plain spectra, cleaner winds, and a knack for carving the first clearings in the fog. Because we have not yet taken a direct, unarguable portrait of a single population 3-star, you might ask how we can speak about their character with any confidence. And the answer is that children carry parents in their features. The very oldest surviving stars in our own galaxy, the ones with almost no heavy elements, but not zero, carry chemical patterns that look like downs from a first generation, strange ratios that point to early factories unlike those of later times. We also read their presence in the way the early universe seems to have warmed and changed, a story told in the faint background of hydrogen's radio whisper, and in the sudden appearance of bright, young galaxies that already needed a push to reach such glow. And though those lines of evidence are careful and humble, together they draw a silhouette we can trust, a set of qualities that fit a universe still learning to shine. All of that is to say that Population 3 is not a myth we repeat for romance. It is a practical label for stars that had to be different, because their ingredients were different. And when you change the pantry, the meal follows. If you want a single image to carry the physics in your pocket, think of snow gathering on a hillside with no trees or rocks to catch it. The drifts will be broad and smooth, fewer in number but larger where they settle. And when the wind rises the first cornices, its shapes will be sharp and bright, dazzling in clean our starlight. The early star, forming clouds, were that bare slope, and the stars were those crisp cornices, pristine and intense, unsoftened by dust. Their light was not the warm lamp of a familiar room, but the white glare of noon over fresh snow, brilliant and tireless, capable of bleaching the landscape and changing the texture of the surface itself. And because their surroundings had no previous smoke, their first ashes stood out sharply, beginning the long project of enriching space so that, much later, smaller, gentler stars and rocky planets could appear. Another approachable way to feel their character is to notice what they were not. They were not metal, rich like our star, so they did not wear the same jewelry in their atmospheres. They were not born into crowded, feedback-filled neighborhoods where older stars had already stirred and heated the gas. So they were not constantly pushed and jostled by previous generations. They were not wrapped in dust cocoons that would dim their light, so their radiation escaped more freely and more fiercely into the dark. In short, they were stars stripped to essentials, a first draft that worked well enough to change the script for everything that followed, and that essential quality gives them their most important emotional trait in this story. They teach the universe how to make stars by doing it the hard way first. You might be tempted to pin a precise age or typical size on them here, but the honest answer is that Population 3 likely covered a family of stars rather than a single narrow type, with the environment deciding details like how large a seed could grow before it lit, how much it spun, and how connected it felt to fresh fuel. The broad brush is what matters in this first meeting, their purity of composition and the consequences that purity has for color, spectrum, winds, and neighborhood. Because those are the traits you will recognize again when you meet their echoes in data and in models. And the practical outcome of all of these traits is simple to state. They were astonishingly effective at changing their world, not because they were mystical, but because clean ingredients, strong gravity, and hard light are a powerful combination. If you want to sense their presence in something you can touch, hold a piece of ordinary iron or breathe in and out and feel oxygen feed your blood, then remind yourself that the first time such elements appeared in any meaningful amount was after stars like these lived and ended. The connection is not sentimental, it is mechanical. The way a kiln makes bricks and bricks make houses. And while the how of their endings belongs to later chapters, it is enough here to recognize the character trait that matters most for the arc of the book. Population 3 stars were the universe's first true builders, simultaneously the first lamps and the first factories, turning a clean, simple sky into a plexity had a chance. To leave this room with clarity, keep a compact list. You can say aloud, born from pure hydrogen and helium. They gathered differently and likely larger because cooling was harder. They shone hotter and bluer, and more simply because heavy element lines were absent. Their winds were cleaner and weaker in the usual way, letting their own gravity shape more of their fate. They carved the first bright hollows in the night, and began to write the first chemical notes into space. And though we have not yet taken their portrait in crisp focus, we see their outline in the faces of their descendants, and in the background's quiet records. Hold that list lightly, and you will be ready for what comes next, because the following doors will open into the specifics of their mass and light, their brief, urgent lives, and the way their first daybreak touched the wider medium. But for now, it is enough to know who they were, the clean sparks that taught the universe to shine. Immense mass and extreme brightness. Think of a match that is so large the briefest strike becomes a blaze brighter than a city. Because the defining surprise of the first stars was not only that they existed, but how much they weighed and how fiercely they shone. And to understand their immense mass and extreme brightness, you do not need heavy mathematics. Only a clear picture of how simple ingredients behave when the universe offers them warmth, space, and time in a particular order. Start with the cloud that makes a star, a pocket of gas that cools as it squeezes. And remember that in this earliest era, the gas had almost no heavy elements or dust, so it could not shed heat as easily or break into many tiny pieces, which meant that when gravity pulled it together, the clumps that formed tended to be larger and warmer than the seeds that make common stars today. A bit like raindrops coalescing on a clean window into big beads, rather than fine mist. That warmth matters, because warmer gas presses back less efficiently when gathered, and it also sets a higher starting mass for any object that can collapse under its own weight. So the first seeds often began their lives already hefty, and once a seed existed, the neighborhood fed it generously. Streams of gas flowed inward along the hidden filaments of the young cosmic web, and the growing starlet gulped that fuel at a rate the modern sky rarely sees, since there were no earlier generations to heat and stir the gas and fewer winds to blow it away. This is how you get a star that does not stop at 10-hour stars or 20-hour stars, but keeps climbing into the dozens, and often the hundreds, with some models allowing occasional giants whose mass might have reached even more, not as exotic exceptions, but as a natural response to a pantry that contained only the basics. Mass by itself is just a number until you pair it with light. And here, a simple rule carries you far. Heavier stars are exponentially brighter because the pressure and heat at their cores rise steeply with size. So a star with 100 times the our star's mass can pour out 1,000,000 times as much energy, not as a gentle golden lamp, but as an intense blue-white beacon that floods its surroundings with invisible ultraviolet photons. And if you prefer a household image, imagine placing a single industrial floodlight in a dark field and watching the ground bleach in every direction. Now multiply that effect until even the thin gas between early clouds feels it. The surfaces of these pioneers ran at temperatures that would make the hottest, modern O-type stars seem modest, so their glow carried enough punch to strip electrons from nearby hydrogen and to break apart the simplest molecules that tried to form. Which sounds technical, but can be held in simple terms. Their brightness carved bubbles around them, where the gas changed state and warmed and thinned, and those bubbles grew and urged until the sky began to patchwork with pale, expanding clearings. In their hearts, that brightness was driven by a core working near the limits of what gravity and radiation will allow, a balance that astronomers call the Eddington edge, where the outward push of light comes close to countering the inward pull of weight. And while you do not need the formal name, the feeling is important. These stars lived pressed right up against what nature lets a star be without flying apart, which is why their light output was so extreme and so steady while it lasted. The same simplicity that gave them their mass also shaped how they held onto it, since their atmospheres lacked the heavy element fingerprints that allow light to push on gas efficiently. Their usual line-driven winds were weaker than those of bright metal-rich stars today, so they did not peel themselves down as quickly and could stay bulky longer while they were still gathering fuel, a detail that sounds small but has clear consequences. A heavier star with a weaker peel remains a heavier star for more of its short span, and so raises the total number of hard photons it will send into space. And those photons matter because they do real work in the young universe. They nudge the clock of the first dawn forward. They set the temperature and chemistry in their immediate neighborhoods, and they act as traffic cops for fresh inflows by altering the very gas that wants to feed the next generation. The human way to feel this without charts is to picture a new settlement that arrives in a cold valley and lights a bonfire so large that the snow around it softens and collapses. The fire does not only give off light to be admired, it changes the ground, it dries some paths while icing others, and it decides which routes will carry more travelers tomorrow. Mass and brightness are not just labels, they are power to rearrange the stage. Because we have not yet caught one of these giants in the act with a clean photograph, it is fair to ask why we are so sure they existed at such scales. And the confidence comes from several gentle lines of reasoning that agree with each other, computer experiments that use the right physics, and only the allowed ingredients consistently form stars whose seeds are large and whose feeding is fast. The oldest, most chemically primitive survivors in our galaxy carry odd ratios of elements that look like the ashes of very massive parents, rather than modest ones. And the way the early intergalactic gas seems to have warmed and changed hints at a sky bathed in hard light that smaller stars could not have supplied in time. None of these lines alone would be enough. All of them together make a calm case, and they do so without asking you to believe in special exceptions, only in the idea that when you remove dust and metals, you change how cooling and fragmentation work, and when you change those, you change the sizes and so the glow. It helps to separate two connected but distinct ideas as you hold the picture. Mass tells you how much fuel sits in the tank, and brightness tells you how quickly the engine burns it. In the first stars, both were extreme compared to most later stars, a big tank being drained by a wide-open throttle. And while we will explore the consequences for lifetime and endings in the next room, here it is enough to notice that such bright engines do not just sit quietly, they constantly flood their surroundings with sharp light and strong pressure, which sculpts the nearby gas into shells and pillars, and sometimes halts further feeding, so that many of these giants were likely built to their mature size quickly, and then fenced in by their own radiance, held within self-carved bubbles like lighthouses inside hollowed caves. This self-limitation is a reminder that nature has checks in place, even when conditions favor bigness. You can only pour so fast before your own output pushes back, which is why there is a spread in mass rather than a single giant size, environment, and timing. Still choose winners within the rules. If you want a number to tuck in your pocket to feel the scale without drowning in detail, keep two friendly comparisons. A star, 30 times the our star's mass, shines tens of thousands of times brighter than the our star. A star 100 times the our star's mass shines roughly 1 million our stars, and the most massive of the earliest likely beat even that. Now ask what 1 million our stars of hard light does to a thin gas that has never seen such intensity before. It does what noon does to frost. It does what a blast furnace does to a thin sheet of ice. It transforms it in place. That is why the discussion of mass and brightness is not an aside for specialists. It is the central reason the universe's first morning arrived as it did, quickly in some places and late in others, patchy and uneven and rich with structure. Because brightness in this context was not a pretty glow, it was an active tool that opened paths and closed others. The cleanest way to leave this topic ready for what follows is to gather the thread without rushing ahead. Immense mass came naturally from clouds that could not easily break into many small seeds, and from generous feeding along early filaments. Extreme brightness followed as a necessary companion, rising steeply with mass and pressing outward almost as strongly as gravity pulled. Inward, weaker winds let much of that mass stay put long enough to amplify the effect, and the net result was a first generation whose light remade its surroundings, rather than merely decorating them. In the next chapter, we will let that throttle setting meet the limits of time and watch what such intensity does to a lifespan. But for now, it is enough to recognize that when the universe finally struck its first matches, they were not timid candles. They were short-lived beacons, built on a grand scale, bright enough to rearrange the dark, short and intense life cycle. If you want to understand why the first stars changed everything so quickly, imagine a life that runs at fast forward from first breath to last word. Not rushed by panic, but propelled by sheer power, because the short and intense life cycle of these pioneers is the natural consequence of starting large and burning hard. And the easiest way to feel it is to think in 3 acts that follow smoothly with no wasted motion: a swift arrival, a brilliant middle, and a decisive exit that leaves the neighborhood transformed. In the beginning, a heavy seed gathers. The exact path to that seed was set before, and we will not retell it here. What matters now is that once a core is compact enough, its own weight squeezes it into heat. That heat invites the simplest fusion to begin, and when the star lights it settles briefly, while the rest of the gas still tries to fall in. The newborn glow pushes back on the incoming streams. A bubble of warm, thin space swells around it, and the feeding slows or stops. So the star quickly finds its mature size and steps onto the main stage of its life. That main act is all about balance. The core turns the lightest fuel into new energy. The outward pressure of that energy holds up the star against its weight. And because the star is massive, the pressure and the heat are extreme, which means the engine runs wide open from the start. First, it burns the easiest route that needs little preparation. Then, as the deep middle of the star creates a pinch of new ingredients, the engine finds a faster lane and the power rises again, you do not need the names of the lanes to grasp the effect. The star brightens and hardens, the color skews to fierce blue-white, and the surrounding space feels a bath of sharp light that peels electrons from atoms and quietly alters every cloud nearby. Living so close to the limit of what a star can be brings side effects that make the story livelier without making it complicated. Many of these giants beat like slow drums. Their outer layers breathe in and out as the struggle between heat and gravity finds a rhythm. Some spin fast enough to stir their own interiors, so that fresh fuel is fed to the core and ash is stirred outward. Some grow as pairs where one can pass material to the other and briefly change both fates. And in every case the same truth holds. The stronger the engine burns, the more quickly the fuel runs down. So their lifetimes are measured in a few bright millions of years, rather than the long calm billions that a modest star enjoys. To keep this friendly picture a candle and a blowtorch. The candle is gentle and lasts an evening. The blowtorch is brilliant and loud and empty sooner. The early stars were closer to the torch in spirit. They did their work fast because their design demanded it, and nature never promised that long life and great impact travel together. The middle act carries a second layer of consequence that reaches beyond the star itself. The unsoftened light digs a hollow in the thin gas around the star, and the front of changed gas moves outward. Shells and pillars form in the neighborhood as the pressure creates structure in material that was once smooth. The small molecules that tried to help clouds cool are broken by the star's glare and then later reassembled in its shadow. Fresh gas that would have fed the star now flows around the bubble toward other seeds. And in this way, a single brilliant life regulates its own growth and also writes a routing map for the next generation, which is why the first dawn of the universe did not brighten everywhere at once, but spread as overlap, in clearings that grew, touched and merged across deep time, a pattern set in part by how short and forceful each pioneer's life was. Inside the star, meanwhile, ash collects where fuel once sat. The core grows heavier and tighter. The outer layers feel the strain, and the whole structure approaches a point where no gentle adjustment will keep the balance. At that moment, the final act begins, and the form it takes depends on how large the star was when the curtain rose. Some heavy stars end with a deep implosion that rebounds and throws their outer parts into space, leaving behind a compact core, and some, even larger ones, find themselves in a more dramatic bind, when the very light inside the core changes character and can no longer hold up the weight. Pressure drops, the core contracts in a heartbeat, and the entire star detonates from the inside out. Not a tidy pop, but a complete unmaking that leaves no inner remnant at all, only a rushing cloud rich in new elements that races into the surrounding dark. For the truly colossal, the end can be quieter for the outside and more final for the inside. The weight overwhelms every support, and the star falls inward to a black hole that keeps its light forever. And though that might sound like an ending that gives nothing back, even that path leaves a gift, because the new dark core can later grow by drawing in gas and become a seed for the bright beacons we see far away in the young universe. You do not have to carry classifications or thresholds to appreciate the point. The specific branch the star takes at the end is decided by size and by how the interior was mixed. But in every branch, the star exchanges its brief time for a change in the world around it. Sometimes it writes a chemical letter into space that future generations read, a signature of how the explosion proceeded that shows up as odd patterns in the oldest stars that survive now. Sometimes it plants a gravitational anchor that will one day power a galaxy's heart. And always it softens and heats the local gas in ways that decide where the next lights will turn on. Even the timing of the exit matters, because the universe was still young and the web still forming. So a star that lived for only a few million years could explode before its bubble touched its neighbors, leaving uneven patches of new material that made some future clouds richer and others poorer. A patchwork that feeds variety into everything that follows, so that the modern sky owes some of its diversity to how quickly the first stars lived and died. The numbers are less important than the rhythm. Quick assembly, bright middle, decisive exit. and each step compresses lessons that map neatly onto a human scale. That speed can be graceful when it follows from design. That intensity has costs that cannot be deferred. That endings can be both loss and bequest. And that the most influential lives are not necessarily the longest. They are the ones that change the field for everyone else. It is also helpful to notice what this short life cycle did not do. It did not make the universe chaotic in a way that erases memory. Rather, it stamped a memory into matter. The products and patterns of these endings were preserved in tiny grains and in the chemistry of later stars, so that even without a photograph we can reconstruct the outline of lives that left so quickly. The past speaking through the quiet composition of the present. When you zoom back out from any single star and watch the whole era, the impression is of a fast dance that turns a silent hall into a festival in very little time. The first lights arrive, they bleach and carve. They end with either a shout that sends new material across space, or a silent fall that plants a heavy seed, and then the next wave uses what was left for them, richer gas where an explosion passed, warm hollows that guide flows, occasional dark cores that will glow later when fed, and so the briefness of each life serves the longer story. A relay in which the baton is not a metal stick, but the conditions that make complexity possible. By the time this act is over, the universe will be ready for stars that live more slowly and for places that can keep solid surfaces and liquid water. But those calmer futures depend on the fast work done here. And that is the cleanest way to remember the first stars. Not only as lights, but as workers who clocked in early, labored at full power, and clocked out soon, leaving behind a world more prepared than they found it. If you want one final image to carry, think of a line of fireworks that do not paint pictures in the sky for long, but instead till the soil and plant a forest in a night. Each flare brief, each flare hot, each flare useful. And when morning finally comes, the forest is already there, because those sparks lived exactly as they had to, fast and intense. Which is why the next step in our story will not linger in their rooms, but will step outside and look at how their short lives flooded the surrounding medium with light and change. The first true illumination of the interstellar sea, the first illumination of the interstellar medium, the first light that truly changed space, did not announce itself with a single our star eyes across the universe. It arrived as a patchwork of local mornings, small, brilliant rooms hollowed out of the darkness inside newborn galaxies. Because when the earliest stars switched on, they didn't just shine, they wrote on the interstellar medium itself, turning quiet gas into glowing geography with walls, doorways, and weather of its own. And to feel what first illumination means, you have to stop thinking of light as decoration and see it as a tool that reshapes matter. Each star carved a clear bubble around itself where surrounding hydrogen lost its electron, and the gas warmed. The edge of that bubble pushed outward like the rind of a growing fruit. And behind the bright edge, the medium changed character from cool, neutral fog to airy, pressurized plasma that actually pushed back on incoming flows. In plain terms, the darkness inside those primitive halos learned new textures. The smooth became lumpy, the lumpy sprouted layers. And those layers mattered, because pressure differences guide motion, and motion decides what can gather and what must wait. In the first minutes of illumination, light reached farther than any sound wave, and did three simple but powerful things at once. It cleaned, it heated, and it sketched boundaries. Cleaning by stripping electrons, so the gas became transparent to more of that light, heating by sharing energy that puffed the gas, and sketching by setting a sharp frontier between changed and untouched regions. A frontier that wrapped around each source like a shell. You can picture these shells without formulas if you imagine a string of lanterns hung in a foggy field. Around each lantern there's a clear, warm pool of air. Beyond it the fog remains, and between the two a thin, active skin, where droplets evaporate fastest. Now swap droplets for atoms and the image holds. Inside those pools, the gas glowed not because it had its own power plant, but because it had been excited and was relaxing, re-emitting some of the star's energy as telltale colors, the strongest of which, born from hydrogen's simplest transition, scattered again and again. wandering before escape and painting diffuse halos around the first neighborhoods of light. So the medium did not just become see-through. It learned to glow on cue like a fluorescent sign when lit from within. Illumination was not gentle everywhere. The same ultraviolet that drew bright rooms also broke apart. The frail molecules that had been quietly helping distant pockets of gas cool and settle. So in the shot, out corridors directly exposed to the first lamps, the chemistry reset to a simpler state and cooling slowed. While in tucked away folds and behind dense knots, shadows protected those molecules and cooling could continue. And that contrast made the earliest star, forming neighborhoods richly uneven by design. Some lanes hardened into bright, warm boulevards where the next peace was postponed. Other lanes, lying in shade, became the preferred paths for new inflow. So the map of future growth was traced by nothing more mystical than light and shadow. Meanwhile, the pressure inside each illuminated bubble drove a breeze from the inside out, sweeping material into thin, dense rims, and when that swept up material cooled it, sometimes collapsed again under its own weight at the shell's edge. A quiet, indirect encouragement from the first stars that could trigger second-generation stars in a ring around their parents. Not because anyone planned it, but because physics likes to reuse its own structures. In this way, illumination both throttled and nurtured new growth, shutting off the easiest routes in the open and making new opportunities in the lee. And that two-handed feedback explains why the first dawn was patchy and why bright did not simply mean more stars everywhere. A town waking porch by porch rather than a stadium floodlight. Inside the bubbles, the gas found a new rhythm. Free electrons made collisions and cooling more efficient in some channels, while the higher temperature made other channels harder. So the medium's ability to shed heat changed in character. And even though these earliest scenes lacked dust and complex elements, the illuminated gas still learned to radiate in specific ways that now serve as its signature, the way a city at night draws lines on a satellite photo along its highways. Later, when the first explosions seeded the medium with new atoms, entirely fresh cooling paths would open, and the palette of colors would expand. But that belongs to a different room. What matters here is that the very act of being lit gave the gas a voice, a set of spectral vowels it could pronounce when excited, allowing us billions of years later to read how strong the first lamps were and how far their rooms had spread, even without the later fireworks. Illumination alone rearranged traffic. Accretion streams arriving along the hidden filaments met the warm pressure in the lit regions and were diverted, shunted into darker lanes that fed outskirts instead of cores. While inside, radiation pressure, light actually pushing on matter, helped carve low-density chimneys, through which future outflows would vent, shaping escape routes for the hot products of endings that had not yet happened. In effect, the first light installed the ductwork for a galaxy's later life. The interstellar medium also learned to carry messages outward, at the borders of lit and unlit gas. Fronts rippled and sometimes drove gentle shocks that wrinkled the fog into sheets and fingers. Familiar shapes you've seen in photographs of modern glowing nebulae, but here made in a sparser, dust-poor environment where edges were crisper and radiation could reach deeper. These wrinkles were not ornaments, they were storage and staging, places where the gas could be briefly compressed, cool, and hold itself together against the background, until the balance tipped and collapse might begin. So, illumination literally built shelves in the dark, on which the next round of structure could be stacked. Over time, many bubbles from many stars touched and merged inside each halo, creating bright commons where shells collided, stirred, and bled into each other. And at those collisions, turbulence blossomed, mixing gas from different neighborhoods, so that what had been a clean single-room laboratory during the long night became a bustling, multi-room workshop with corridors and courtyards, and a preferred circulation. This mixing mattered because it smoothed away some of the extreme contrasts the first lamps had created, while preserving enough pattern to guide future growth. A compromise between order and variation that living structures always seem to need. It is easy to confuse this interstellar story with the later, grander tale in which the universe's large-scale fog is cleared between galaxies. But keep the scales straight. The first illumination we are tracing here is an indoor event, inside the earliest small galaxies, room by bright room, where local gas learned how to be a neighbor to light. Only much later, when enough rooms exist and enough doors are knocked through their walls, does the glow leak into the streets between buildings and begin to change the entire town. This chapter is about learning what a lit room feels like, how it breathes and where it sets its furniture, because those choices decide how the house can grow. And if you ask how we can know any of this without a time machine, the answer is that the gas itself left clues in the faint halos of scattered light around very distant galaxies, in the way the youngest visible systems seem wrapped in soft, extended glows rather than sharp sparks, and in how the statistics of those glows change with distance in a way that matches rooms growing, touching, and sometimes being muffled by leftover force, radio maps and careful models. Add a second line of evidence by showing that patches of the early sky must have been warmed and thinned, in just the manner illuminated bubbles predict. And while every individual clue is shy, together they draw an outline consistent with the simple picture. Light makes rooms. Rooms make winds and shells. Shells make chances. If there is a single memory to carry forward, let it be the humility of light's first job description, not spectacle, but carpentry, cutting cavities, bracing walls with pressure, knocking through passages, and marking surfaces with lines. We can read long after the builders are gone. And because the first stars lived fast, these renovations happened in a rush, so that by the time their brief lives ended, the surrounding medium was no longer the same place that welcomed them. It was a taut and textured environment ready to host different kinds of stars under different rules. Stand in that room for a breath, and you can feel why the next part of our story turns inward instead of outward, because to understand how a room can be lit so powerfully, you eventually have to step behind the door marked Engin, into the star itself, where the plainest ingredients are set on fire, in layers, and the lamp that writes on space is born from a furnace we have not yet visited. From hydrogen to helium, the star's first furnace. A star is not born with a flame already lit. It learns to make its own fire by pressing the simplest stuff in the universe so tightly that the ordinary rules of apart and together start to blur, and in that blur hydrogen becomes helium, the star's first furnace, turning a slight loss of mass into a flue of light that holds the whole sphere up against its own weight. Picture the beginning without jargon. Gravity gathers a cloud until the center is the most crowded room nature can make without breaking the furniture. Crowding means heat. Heat means the particles move fast, and fast motion makes them try to touch even though their like charges shout. No, if you tried to push two tiny magnets together the wrong way and felt that springy resistance, you've met the star's problem. Yet in the deep core, the no isn't final, because matter is not only billiard balls but also waves. And waves can overlap, so once in a rare, while two protons drift so close that their fuzzy edges sneak through the electrical wall. This is quantum tune. Nellaling in friendly clothes, and that tiny permission is enough. A chain begins where lightest becomes slightly heavier, and the difference in mass is not lost, but paid out as energy according to a simple promise of nature, E equals m times c squared. The core does not explode when it lights, because stars come with a built-in safety feature. A thermostat written into physics. If the core gets a little hotter, the reactions run faster, pressure rises, the star puffs up, cooling the core and slowing the fire. If the core cools, gravity tugs a little tighter, the center heats, and the fire returns to pace. This give and take is called hydrostatic balance in textbooks, but you can call it common sense. The push of light and hot gas inside exactly matches the pull of weight outside, and it is the reason a star can shine steadily for a very long time without either collapsing or tearing itself apart. In the smallest sketch, the first furnace works in two flavors that depend on how hot the center gets. In our star-like and smaller hearts, Hydrogen fuses mostly through a patient route, where two protons become a deuterium latch. Then helium follows after a few steps, each step releasing a little light and a shy burst of neutrinos that leave immediately, messengers no wall can stop, in hotter, heavier hearts. Like many of the first stars we met, there is a faster loop that uses tiny amounts of carbon, nitrogen, and oxygen, like a set of reusable tools, catching and handing hydrogen around until helium drops out, and the tools are returned to the start. Ready again, a catalytic dance, whose only real fuel is still hydrogen. You do not need the step names to grasp the contrast. One path is a slow walk, the other a sprint, and the sprint speed means that a small rise in temperature can multiply the fire many times over, which is why the giants we've described burn so intensely and live so briefly, yet whichever path a given star prefers, the outcome is the same in spirit. 4 light pieces become one slightly heavier piece. The small mass difference pays the star's bills, and the bills it pays are everything you can see: brightness, color, the pressure that keeps the star round, the warmth that sets the tone of the whole system around it. Energy made in the core does not leap straight to space for photons. The light quanta, the trip outward is a long crowd shuffle, a random walk through layers where they are absorbed and re-emitted countless times, turning a straight sprint into a maze that can take ages to cross. So the light you finally see from a calm star's surface began its journey when history was younger. While neutrinos from the same reactions pass through the star in a heartbeat, indifferent to matter, a reminder that nature ships energy by both post and express. In some stars, rising hot blobs carry part of the heat outward like boiling water. In others, radiation alone does the job, and the choice depends on how steep the temperature gradient must be to carry the flow. But you can hold the essence without schematics. A star is a layered orchestra, moving one melody from its hidden core to the sky, and each layer plays its part so that the tune arrives smooth to our eyes. The chemistry of the furnace changes the star's body language over time. As helium ash piles up in the center, the core becomes denser and less efficient at supporting itself with the same gentle pressure. The star adjusts by shrinking the core a little and brightening the envelope a little. And those small shifts change color and size, in ways you can watch across a lifetime, if the star is massive enough, and you are patient enough. None of this requires magical switches. Only the logic of fuel and ash, where fuel remains, light remains, where ash dominates. The scene must change. And that slow change is the bridge that will carry us, in later rooms, to second furnaces, that light only when gravity has squeezed the core enough to demand a new strategy. It helps to keep one clean mental model as you leave this first furnace. Imagine a heavy, restless crowd kept from collapse by music, so strong it lifts them from within, and every beat of the music is paid for by a handful of coins shaved from the crowd's mass. The coins are tiny, the beat is steady, the lift holds, and as long as pockets of hydrogen remain near the center, the song continues. This is why modest stars can glow for billions of years, and why giant ones run through their first act in a few million. A faster song spends coins faster. And it is also why the light on your face, when you stand in our star, is not a surface trick, but a deep accounting sent from a pressurized heart. Your life already carries the receipt. Each breath depends on warmth, born in a chain of near misses, in a place you cannot see, and each morning's light is the interest paid on mass, turned into energy at a rate so gentle you can watch by seasons instead of seconds. If you want one last plain sentence to carry forward, let it be this. The star's first furnace is the art of turning togetherness into light. Light hearts joining as one heavier heart, and the tiny missing sliver becoming the pressure that holds a world in daylight. And when that art finally begins to fail in a core filling with helium, the story does not end. It changes key, inviting the next layers of the stellar engine to learn new steps, while the universe learns new colors of light. A handoff we will open in the following chapter. The production of carbon, oxygen, and heavier elements. When a star outgrows its first kind of fire, it doesn't go dark, it changes the recipe, And the next recipe is the one that makes you possible. Helium turns into carbon, carbon into oxygen, and in the hotter hearts of the biggest stars, the ladder keeps climbing toward a whole pantry of heavier elements. So if the previous chapter was about learning to breathe, this one is about learning to speak in sentences, joining simple syllables into words with meaning. The moment hydrogen runs low at the center, the core loses some of its gentle support and gravity nudges it inward. Inward means hotter, and hotter opens a new door, because helium, that once bounced apart, now has enough energy and crowding to do something rare. 3 helium nuclei come together almost at once to make a carbon nucleus. That 3 at a time trick would be impossibly unlikely if nature hadn't left a helpful rung in the energy ladder. A sweet spot that lets 2 helium pieces linger together long enough for a third to join, like a note that resonates so a second singer can find it. And the result is carbon, the flexible backbone of life's chemistry. The star has, in effect, discovered a second furnace, one that lights at higher temperature, and a new balance is struck. The fresh heat from helium burning pushes back against gravity, and the core rests again for a while. This time paying its bills, not by turning 4 hydrogens into 1 helium, but by stitching helium into carbon, and, soon after, into oxygen. When a carbon piece grabs another helium, you don't need the nuclear notations to feel the flow. Small becomes medium, medium becomes a bit larger, and each step gives off energy that helps the star hold its shape and shine. The practical consequences of this new fire are everywhere you can look, even on your kitchen table. The carbon that frames your cells and the oxygen that partners with hydrogen, in every glass of water, both trace to this phase of stellar aging. How much of each a star makes depends on conditions in the core, especially the exact pace at which carbon can grab helium to become oxygen. A pace that acts like a hidden dial. Set it one way and more carbon survives. Set it another and oxygen wins. And that quiet dial later shapes what kinds of planets and rocks can form from the ashes, which molecules are easy to assemble in clouds, and how hospitable a young system might be to the chemistry we care about. Stars like our star are slow, safe factories that reach helium burning late in life, swelling into red giants whose cores grow hot enough to make at least some carbon and oxygen, before gentle winds carry those new elements outward. More massive stars, born with deeper gravity and fiercer heat, not only make abundant carbon and oxygen, but carry on to hotter furnaces that add steps, carbon fusing with carbon to yield neon, sodium, magnesium, then neon rearranging, then oxygen fusing to make silicon and sulfur, then silicon shuffling its pieces into a blend that leans toward iron. Like nuclei, each stage lights only when the core becomes hot enough for that specific reaction, and each stage runs faster than the one before. So a massive star spends millions of years on hydrogen, hundreds of thousands to 1 million or so on helium, and then burns through the later fuels in mere thousands, then hundreds, then days, an accelerating sprint you can feel without learning temperatures. More heat opens the next door, and behind each door the fuel is scarcer, and the clock runs quicker. It helps to remember that stars are not empty chemistry sets. The byproducts of one step change the behavior of the next. Whenever the core assembles new, heavier nuclei, the average particle count per bit of mass goes down. The gas supports itself less easily at the same temperature. Gravity squeezes harder, and the star responds by heating further and shrinking the burning region, which in turn makes reactions more sensitive to every small change. This is why the road from helium to oxygen and beyond is not a leisurely country walk, but a series of short ascents, each steeper than the last, and why the details of mixing inside the star, how fast fresh fuel can be fed to the core and ash carried away, matter so much. In some stars, rotation stirs the pot. In others, slight pulses do. In others, close companions trade material and shuffle the deck. But the broad idea is the same. The engine learns new tricks as it ages, and those tricks decide what will be in the ash the star eventually returns to space. Not all of the universe's heavy elements are forged in the steady heat of these core furnaces. Beyond the iron, leaning mix, making still heavier nuclei stops paying energy back, and starts costing it. So nature uses a different shortcut in later chapters. It throws neutrons, uncharged particles that slip easily into nuclei, at existing seeds, and two broad tempos emerge that you can hold in plain words. The slow, patient tempo happens in swollen, elderly stars that have gentle internal fireworks and lots of neutrons to spare, adding them one by one with time for the nucleus to settle between captures. This slow path builds elements like strontium, barium, and lead, and the same bloated stars often become carbon stars. Their surfaces so rich in freshly made carbon that their winds thicken with dust and carry soot into space grain by grain. The fast, stormy tempo happens when a dying massive star or a pair of dense stellar remnants floods nearby matter with neutrons, so quickly that seeds grab them in bunches before they can settle. A brief, furious rain that jumps the periodic table upward to rare, precious species like gold, platinum, and iodine. Both tempos write their signatures into the oldest surviving stars and into meteorites. So when we analyze those ratios in the lab, we are reading a diary of nuclear weather from long before Earth existed. The gentle miracle is how all these products leave the workshop and become part of the wider world. Because a star does not keep what it makes. In the helium, burning phase of modest stars, the atmosphere grows loose and dusty, and is lifted off by starlight and pulsations, enriching the surrounding gas with carbon, bearing material that will later help clouds cool and form new stars and planets. In massive stars, much of the ash stays locked up until the end, when a violent change, saved for another chapter, throws the inner layers outward at high speed, mixing carbon, oxygen, silicon, and more into the interstellar medium where they cool, condense onto grains, and begin the slow cycle of assembly all over again. This is why the second and third generations of stars are born easier than the first. The gas they form from already contains efficient coolants and solid surfaces to help tiny pieces stick. And this is why rocky planets, water, and the chemistry of life are latecomers in a universe that began with almost nothing but hydrogen and helium. If you want to keep the picture human-sized, think of a bakery that starts with flour and water, and only later acquires sugar, oil, spices, and fruit. Early loaves are plain and few. Later loaves are abundant and varied because the pantry is richer and the oven learned more recipes. Carbon and oxygen are the sugar and oil of cosmic cooking, making it easier to shape the dough of gas into stable structures, giving clouds more ways to shed heat, and offering surfaces where simple molecules can practice. By the time those ingredients are common, the galaxy smells different. There is more dust to dim the brightest light, more paths for chemistry to explore, more chances for planets with solid crusts and deep oceans. None of that requires magical thinking. Only the patience to let many generations of stars run their fires and share their ashes. The gentlest, truest sentence to carry forward is this: stars are factories that discover new kinds of fire as they age, and those fires make the very elements that later become clouds, worlds, oceans, rocks, and breath. Helium burning makes carbon and oxygen. Heavier burning in massive hearts builds a ladder toward iron. And beyond that ladder, special storms spray neutrons that climb to gold and iodine. The details matter to specialists. But the arc is friendly enough for anyone. Simple stuff learns to join in new ways when it is pressed and heated. And what cannot be made in steady heat is made in rare bursts. When you look at a leaf, a ring, a sip of water, you are looking at the cooled light of those furnaces, the stored memory of reactions in the deep that turn togetherness into energy and then into matter with new possibilities. And when the next chapter opens, we will step from the recipes to the kitchen layout, seeing how these different fires settle into layers inside a massive star, each one stacked above the next like floors in a living factory, until the building reaches its natural limit. The onion layer model, the star's internal structure. If you could slice a massive star cleanly the way you cut an onion, you would not find a single uniform fire, but a stack of working kitchens, each floor cooking a different recipe at a different heat. And this layered interior is the simplest, most powerful way to understand how a star organizes itself. Once the first fuel is running low and new fires must be lit deeper inside, gravity and temperature write the blueprint without asking our permission. As a star ages, the ash from one furnace is heavier than the fuel that made it. So it settles toward the center, and the core contracts a little. Contracting raises the temperature and pressure at the very heart. And that extra heat opens the next doorway for fusion, while the old fuel continues burning in a shell around it. So the star naturally builds rings, a hot new core cooking a fresh ingredient, wrapped by a shell where the previous ingredient is still being consumed, wrapped again by cooler layers that are not yet hot enough to join the work. In a star like our star, this starts modestly, with a helium core and a thin hydrogen-burning shell that puffs the outer layers into a giant. But in truly massive stars, the scheme becomes a nested set of furnaces. A helium-burning core surrounded by a hydrogen shell at first. Then, as helium in the very center is used up, the core shrinks and heats until carbon can burn there, and the spent helium burning moves out to a shell. So the onion gains a new ring. Later the same dance repeats with neon, oxygen, and silicon in the core, while the older fuels move to shells wrapped around them. And the result is a cross-section that looks like a tree trunk of rings at different temperatures. Each ring with its own rhythm, each ring paying part of the bill that holds the star up against its own weight. The reason the layers stay mostly separate is not mysterious. It is simple physics and buoyancy. Heavier mixtures prefer the center. Lighter ones float above, and the temperatures needed to run later reactions are so high that only the very inner regions can reach them. So the furnace for a given fuel sits where the thermometer allows it and nowhere else. Yet the onion is not a rigid stack of glass plates. It is alive and moving. Edges blur and migrate. Shells switch on and off as conditions change. Waves pass energy across boundaries, and turbulent regions stir their contents like spoons in a pot. Some layers are calm and transport their heat by passing photons hand to hand in a slow relay that we call radiative. Other layers boil. Hot blobs rise, and cool blobs sink the way water rolls in a simmering pot. And that convective motion mixes fresh fuel inward and ash outward, thickening the ring and making the boundary fuzzier. Whether a given layer is radiative or convective depends on how steeply the temperature must drop to carry the light through that material, which in turn depends on what the material is made of and how tightly it holds on to passing photons. And in very massive stars, the deepest burning zones often become convective, because the energy flow is ferocious, and the material is opaque enough that radiation alone cannot carry it. Rotation adds another gentle complication that you can picture without formulas. As the core and envelope spin at different rates, shear stretches and winds up magnetic fields along the boundaries. Those fields can tug on the gas and move a little material across layers. A quiet smearing that changes the exact thickness of each ring and helps feed fresh fuel down to the center, prolonging certain phases and altering how the star will behave later. Even with these shadings, the onion picture stays true, because the big idea is about hierarchy and access. The hottest work is in the center. Older work moves outward into shells, and the cooler outskirts are storage, staging, and insulation. Each ring has its own thermostat and timescale. Hydrogen burning in a shell can run for a long time and is gentle in its response. Helium burning in the core runs hotter and responds more dramatically to small changes. Carbon and oxygen fires deeper in, are shorter lived and more sensitive still, and by the time silicon is burning at the center, the thermostat is barely keeping up. So small shifts in heat can lead to pulses and breath-like contractions that ripple outward to the envelope, changing a star's size and brightness in ways we can actually detect from far away. This ladder of timescales is why the inner rings evolve faster than the outer ones. A star can spend millions of years with a hydrogen shell, hundreds of thousands with helium in the core, and then race through the deepest fuels at a pace that would look like mere moments by comparison, which makes the onion a living time machine as well as a map. The state of the inner rings tells you what the star has just done and what it will try next. The star's light must climb through all these rooms to reach space. and that journey itself shapes the layers. Because photons scatter and are re-emitted many times, loading some layers with a strong outward pressure, while in the very hottest, densest inner floors another carrier begins to matter. Ghost-like neutrinos that slip through matter, almost without touching it, start to carry energy away directly, draining the heat from the center faster than photons can. And that invisible leak encourages the deepest core to contract sooner and more sharply than you might expect if you thought of light alone. You do not need the particle names to feel the consequence. The inner thermostat changes its personality. The core acts less like a well-insulated oven and more like a stove with a hidden draft, forcing the next stage to begin earlier and tightening the spacing between inner rings. This living onion is not something we see by cutting open a star in a lab, but it leaves fingerprints we can read honestly. When a massive star ends violently and its layers are thrown outward, the different elements emerge at different speeds and glow at different characteristic colors. And by studying those patterns, we can reconstruct which rings were where before the end. Even in gentler stars, faint tremors travel through the interior and slightly modulate the light we receive. And by measuring those tiny rhythmic changes with patient telescopes, we can perform a kind of ultrasound that tells us which layers are dense, which are buoyant, and how thick the rings might be. In meteorites, we sometimes find microscopic grains that condensed from specific layers in long dead stars, their internal atomic accents matching the environments we expect in particular shells, a tangible speck from a single ring in the stack. These are not romantic claims. They are practical ways of testing the picture, and together they support the idea that onion structure is more than a metaphor. It is a working description of a star's interior after the first furnace has handed the baton to deeper ones. The most helpful way to hold the onion in your mind is as a factory with floors, not a museum with display cases. Because the floors talk to each other through pressure and gravity. When the core changes pace, the shell above it notices. When a shell adds heat, the envelope responds by swelling or settling. And when a boundary moves inward or outward, it changes the supply lines for its neighbors. These conversations are why the outside of a massive star can drift from a compact, bright blue personality to a bloated red one and back again, even though the star is the same object, because a small rebalancing between inner floors changes the pressure at depth, and the outer skin must find a new radius that keeps push and pull in equilibrium. In the first stars of our story, which lacked dust and heavy elements, the onion's outer skins were unusually transparent, and the inner pressures unusually high. So their floors ran hot, and their light carved clear rooms in the gas around them quickly. But that was an environmental detail layered on top of the same interior logic we are following here. Keeping the picture simple is the key to making it useful. Ash sinks. New fires light deeper in. Old fires keep burning in shells. Hotter steps live inside cooler ones. And the whole stack is held together by a delicate equality between outward pressure from heat and light and inward pull from gravity. As long as each floor can pay its part of the pressure bill, the building stands. The lights stay on, and the onion grows new rings one by one. When you carry this forward to the next chapter, you will see why there is an inner limit to this architecture. Because eventually a core made of certain tightly bound nuclei cannot pay the bill by lighting a hotter fire. And when that happens, the balance we have been admiring falters. Not because the star forgot how to build layers, but because nature's ladder runs out of rungs at the very center, and the onion must face a decision it cannot solve with another ring: the iron barrier. The point where fusion stops. There is a point in a star's life when adding more heat stops helping. A locked door at the very center where the usual recipe, press things together and get light out, suddenly fails. And the simplest way to feel that door is to think like an accountant rather than a romantic, up to a certain kind of nucleus. Fusing lighter pieces into a heavier one pays a profit in energy. But once the core fills with iron, family nuclei, the bookkeeping flips, and every attempted fusion would cost energy instead of earning it. Profit becomes loss. The furnace can no longer pay the pressure bill that keeps the star propped up, and the building begins to sag from its own weight. Why iron? Not because the universe likes that metal in particular, but because of how snugly different nuclei hold themselves together. As you climb from hydrogen to helium to carbon and oxygen and on through the ladder in a massive star's heart, each rung gives you more binding value per Pascal radical, like trading a few loose coins for a tightly rolled stack. Energy is released, and the core glows near the iron group that binding curve peaks, meaning the rolls are as tight as nature makes them under steady conditions. So trying to go heavier is like pushing a ball up a hill after a long run downhill. You must add energy rather than receive it, and a star has no bank account for that. It only knows how to earn, not how to spend, to hold itself up. In practical terms, when the inner factory has marched through hydrogen, helium, carbon, neon, oxygen, and finally silicon, the new ash it makes is iron, family material, and that ash behaves like a perfect insulator against further burning. It neither adds heat by fusing upward, nor can it be split in a way that gives back more than it takes. For a brief moment, the star muddles through with shells still burning above the iron core, hydrogen farther out, then helium, carbon, and so on. But the center, where support matters most, has switched off as a source of pressure. Two quiet thieves now step forward and make the problem urgent. The first thief is light itself, which at these desperate temperatures becomes so energetic that some photons turn from helpers into wreckers, smashing iron nuclei back into smaller pieces, alpha particles, and lone protons and neutrons. In a process that soaks up energy rather than releases it, it's as if the core starts burning its furniture just to stay warm, only to discover that the act of breaking the furniture chills the room further. The second thief is the sea of electrons that has been shouldering more and more of the load. At astounding densities, those electrons behave like a stiff spring, a pressure that doesn't depend much on temperature and has been quietly keeping gravity at bay while the last fuels were consumed. But as the core grows and squeezes, some of those electrons are forced into protons, turning them into neutrons, and giving off neutrinos that escape straight through the star. Every electron captured this way removes a bit of that spring and carries energy out the door. Two losses at once: support and heat, because the core can no longer brighten by lighting a new fire, and is now being cooled and unsprung from within. Its collapse is not a leisurely settling, but a sudden surrender. The iron-rich center grows toward a critical weight, reaches a point where no known pressure can hold it in that form, and then drops inward in a fraction of a second, dragging the layers above with it like a stage floor giving way beneath the set. You don't need the specialist names to grasp the rhythm. Downhill profit, then a flat, then an uphill that a star cannot climb. Switches that used to stabilize now destabilize. Supports that used to strengthen now vanish when leaned upon. The iron barrier is, in that sense, not a wall you hit so much as a cliff. You suddenly realize you've already gone over, because once silicon burning has finished stocking the center with iron family nuclei, the options run out. No next rung to light, no gentler fuel to switch to, just gravity asking for a payment the core cannot make. This change also explains a puzzle that might have bothered you earlier. If the universe has elements heavier than iron, and fusion can't make them inside a calm core, where do they come from? The answer is that nature changes the rules of the game only in rare storms. When the star dies or when dense remnants collide, and uses a different pathway that doesn't rely on steady heat, earning fusion at all, it floods existing seeds with neutrons so quickly that the seeds climb the periodic table by capture rather than by squeezing later, decaying into stable heavy elements. In other words, the iron barrier ends the quiet factory's work, but it does not end the story of heavy elements. It hands that work to the fireworks. Returning to the star at the brink, the emotional truth of the iron barrier is almost tender. For millions of years, the core has solved every crisis by learning a new way to shine. Each time gravity tightened its grip, heat found a new recipe and pushed back. And then one day the repertoire is complete. When a locked door finally appears at the center, the star does not fail because it is weak. It fails because it has been too successful at turning lighter things into tighter things. And now the very perfection of that tightness forbids further profit. This is also why the last stages before the barrier feel breathless on a cosmic clock. Hydrogen burning may last millions of years, helium hundreds of thousands, but silicon burning tumbles to completion in days. The thermostat is frayed. The neutrino leaks are wide open, and the core races to a composition that leaves it with no cards left to play. Everything you can see from far away in those final days, the shifts in color and size, the subtle pulsations, is the outer envelope trying to respond to whispered messages from a center changing too quickly to explain itself. If you want a home-sized metaphor to carry this forward, imagine a skyscraper whose lower floors provide power for the whole building. As each generator room wears out, a newer, deeper room takes over, and the building hums along. But in the deepest basement there is one last room that can only store power, not make it. Once the operation reaches that floor, the meters still show weight pressing down, but the needles for income fall to zero. The structure has seconds to live. That is the iron barrier in plain clothes. A bookkeeping flip that becomes a physical catastrophe. An energy economy that turns from exporter to importer, at the one place where imports are impossible. The next step, the sudden inward rush, the central snap back, the shock that races outward through the onion of shells, the blast or the black hole, belongs to the following chapter. For now it is enough, and more respectful to the physics, to stop at the locked door and understand why it is locked, because the best way to hold a nucleus together peaks at iron. Because beyond that peak, the star would have to spend energy it doesn't have. Because its last reserves are quietly stolen by light that unbuilds and by electrons that vanish into neutrons. Because gravity is patient and pressure is finite. And if you're looking for a human-sized lesson in this cosmic limit, it is this. Even the brightest engines have honest boundaries, and knowing where they lie is not defeat. It is the first true understanding of what comes next. Core collapse and the great explosion. Some endings do not arrive like winter. They snap like a rope under too much load, and a massive star's final moment is exactly that. One instant of quiet strain, then a sudden giving way in its deepest room that triggers the greatest explosion a single star can make. And you can understand it cleanly without chasing equations if you follow the sequence as it actually unfolds. Once the very center can no longer support the weight above it, the innermost core begins to fall inward, not drifting but plummeting, its size shrinking from something Earth-like to something city-sized in less than a heartbeat. And as it does, the material outside races to follow. The collapse heats and squeezes the heart to densities where the matter there behaves more like one continuous substance than a gas of individual particles. And at that point, the infall slams into a stiffness that nature will not let you compress further. The way a fist meets a locked door, the core halts and rebounds ever so slightly, sending a shockwave outward into the rain of still, falling layers. And for a fleeting moment it looks as if that shock might blast the star apart by sheer momentum. But the layers raining in are heavy and dense, and the initial shove spends itself quickly doing hard work. So the shock stalls like surf that breaks and curls back on itself just short of the beach. If the story ended there, the star would simply swallow its own crash and fall dark. Yet something profound is happening in the invisible channel at the same time. The newborn compact heart, a hot, dense object only a few tens of kilometers across, is pouring out an unimaginable flood of ghost-like particles that pass through almost everything, neutrinos, carrying away nearly all of the gravitational energy released by the collapse, far more energy than the light we will ever see from the event. Most of those ghosts sail through the star and keep going into space, but a small fraction hit the material just behind the stalled shock, sharing enough of their energy to reheat and repressurize that region. And in the churning, turbulent flow, helped by rising plumes and sloshing motions that stir and refeed the hot spot, the shock finds fresh strength, pushes outward again, and finally clears the star's outer rooms. This revival is delicate and chaotic when seen in computer experiments, but simple to hold in your head. The first punch wasn't enough, So the deep heart paid in a different currency that only partly interacts, and that partial payment was exactly what the stalled front needed to get moving again. When the shock breaks free of the surface, there is a moment like a flashbulb. The sudden escape of buried light called shock breakout. That races ahead and announces the disaster to the wider universe. Within hours to days, the star brightens into a beacon visible across galaxies. Its light not from the original punch, but from the energy trapped and rerouted through the expanding debris, and later, from the slow glow of newly forged radioactive material mixed into the ejector. One of those fresh isotopes, a particular version of nickel, decays step by step into cobalt and then iron, and the heat it releases acts like a long, fading ember that keeps the wreckage shining for months, powering the graceful decline you see on a supernova's light curve. As the hours become days and weeks, the expanding shell thins and turns translucent, letting us read the speed and composition of different layers. By the way they absorb or emit certain colors. Hydrogen lines for one class, their absence for others, fingerprints of oxygen, calcium, and more. So a distant telescope becomes both clock and chemical lab, allowing us to reconstruct the ordering of the blast without a single equation on the page. Not every collapsing star takes the same exit. If the collapsing heart is light enough, the rebound forms a stable, city-sized ultra-dense object that packs more mass than the Our star into something the width of a county, a neutron star, whose magnetic fields and spin can later sweep space like lighthouse beams. If the heart is heavy, still, the inward rush may never be arrested strongly enough to form a permanent surface at all, and the star's core continues past invisibility into a black hole, with the outer layers either failing to escape or, in some cases, being hurled outward by jets launched during the birth of that black hole. The origins of certain rare, high-energy bursts we catch only when pointed straight at us. The details vary with mass, rotation, and companion stars, but the skeleton of the story is sturdy. A sudden inward fall, a shock that stalls, a deep reservoir of ghost energy that relights it, and either a compact remnant or a darker end. How do we know any of this, and not just retell a clever tale? The universe has already sent us receipts in several languages. In 1987, light from a nearby galaxy delivered a supernova whose photons we watched unfold night after night. And crucially, underground detectors on Earth pinged with 2 quick bursts of neutrinos, arriving hours before the visible brightening, just what you would expect if an invisible flood escape did the newborn heart long before the shock reached the surface. Across the sky, delicate ripples of starlight in the remnants of ancient blasts. The crab, the vela shell, more show filamentary knots and expanding rings that match the physics of a shock, ploughing through layered material. And in laboratories we have built the math into code and let the star collapse inside a computer, discovering that the revival is not a straight push, but a dance of upwelling hot plumes and sideways, sloshing that helps neutrino heating stay in the right place long enough to win, an explanation that predicted features later seen in the asymmetries of real explosions. If you keep your language plain, the meanings are friendlier than the jargon. The explosion you see is really the surface signature of a deep negotiation between gravity and pressure, coursing through matter in its most extreme mood. The power that unbinds the star is tiny compared to the total energy budget. Most of the energy leaves as those near invisible neutrinos, but even a tiny fraction is plenty to fling the outer layers into space at thousands of kilometers per second. The bright show is only the top of the ledger, and the heavy work is done by particles. You cannot stop with a light year of lead. The consequences for the neighborhood are immediate and lasting. The blast front sweeps up surrounding gas into a shell that glows for centuries, seeding the area with the elements synthesized in the star's final hours. The shock's pressure wrinkles the nearby medium into filaments and knots that can later collapse again into new stars. And the compact remnant, if one remains, anchors the center with gravity, and sometimes with radiation, pulses, winds, that continue to sculpt the environment long after the fireworks fade. That is why a single supernova can be both an ending and a gardener clearing, stirring, and fertilizing the ground for the next generation. You might expect a disaster on this scale to be simple in appearance, but real blasts are lopsided. The outgoing debris often shoots faster in one direction than another. The remnant receives a kick and races off through space at hundreds of kilometers per second, and the chemical layers mix in messy ways that leave clumps of newly minted elements far from where a tidy, symmetric picture would place them. This asymmetry is not a flaw in the story. It is the story turbulence and sideways motions in the tiny region behind the stalled shock turn the revival into a chaotic engine, and chaos writes asymmetry into the sky. That messiness is a gift to us, because it lets astronomers tell which way the explosion leaned and how the internal boiling behaved by studying the shapes of young remnants. On human scales, the times are startling. The inward plunge finishes in less than a second. The outbreak of light takes hours to days. The visible peak glows brighter than an entire galaxy for a week or two. The slow tail fades over months as the radioactive ember cools, and the remnant shell grows and cools for thousands of years. When you look at a faint, expanding ring in a long exposed image, you are seeing a frozen shockwave still traveling outward from a single second of decision in a star that died before our species had language. There is a quiet, personal lesson nested here that does not shrink the science. Systems can endure for a very long time by adjusting stage by stage. But when the available tools are exhausted, the change that follows is sudden, and the aftermath is not just ruin, it is rearrangement. The elements that will someday sit in rings and bones and oceans are carried outward in that rush. The dust that will seed new chemistry condenses in the cooling wake, and the fixed points by which galaxies steer, the compact hearts at their centers, the fountains of high-energy light, sometimes begin with this same surrender at depth. So when you hear the phrase, core collapse and great explosion, don't imagine chaos for its own sake. Imagine a swift, stern conversation between gravity and a star that has run out of ways to hold itself up. A conversation decided in a blink and announced for months, written in light you can see. In neutrinos, you can barely catch, in ripples of space. Time we are just beginning to listen for, and in the quiet enrichment of the cosmic neighborhood that will make gentler worlds possible, and carry forward this single sentence as the bridge to the next chapter. In the instant a massive star fails at its center, it succeeds at something larger by scattering the material of future places, turning a collapse you cannot witness directly into an outward gift you will one day hold in your hand, the formation of heavy elements in the final blast. Endings rarely make things, but a star's final blast is an exception, so bold it rewrites your sense of cause and effect. What looks like a ruin is, for a few breathless seconds, the most productive factory the universe knows. And if you want to see heavy elements born, those stubborn entries on the right-hand side of the periodic table that your rings, rocks, oceans, and neurons quietly depend on, you have to stand just behind the shock as it tears through the star's interior and turns ordered layers into a storm of opportunities. The recipe is easy to say, even if the conditions are extreme. The shock heats each passing shell to unimaginable temperatures, crushes it, and then lets it expand and cool so quickly that nuclei are forced into new arrangements before they can think of unmaking themselves. A time-limited market where only the fastest trades clear. In the oxygen and silicon rich zones, the heat is so fierce that matter briefly forgets the details of which element it was and sits in a statistical mixture dominated by free particles and alpha pieces. Then, as the material expands, those parts snap back together into new selections. Iron, group species like nickel and cobalt among them, an explosive burning phase that finishes in heartbeats and leaves behind the very isotopes that will later power the visible glow of the supernova as they decay. A little farther out, where the shock is still hot, but not quite as brutal, lighter nuclei are rearranged into intermediates. Calcium, titanium, chromium, while in pockets with slightly different densities, a surplus of free helium pieces persists long enough to glue themselves onto heavier seeds. In quick succession, a pathway nicknamed alpha-rich frees out that enriches the mix with elements such as zinc and some rare stable nickels you hardly notice, until a lab spectrum whispers their names back to you. None of this requires you to memorize temperatures. Just hold the rhythm, slam, scramble, snap, and set. 3 verbs in a hurry that produce a new cast of atoms from the material the star had been stockpiling in quieter times. Yet the shock's chemistry is only half the story, because the newborn compact heart, the city-sized object left at the center, spills out a flood of nearly untouchable particles, neutrinos, whose numbers are so enormous that even their shyness matters. These ghost messengers wash through the just processed layers and, by bumping into an occasional proton or neutron, tweak the local balance between the two. And that balance decides which assembly line will run in the fleeting wind of matter that blows off the surface. If neutrons outnumber protons by enough, and the expansion is swift, there is a frantic, nearly assembly, line capture of neutron onto existing seeds, and our process rapid. Because there is no time to pause, stacking neutrons so quickly that the nucleus grows heavy before it can settle, later decaying into stable elements far up the table, including precious things like silver and gold and necessary things like iodine. If instead the wind is tipped slightly toward protons, a different route opens in the same few seconds, the fact process, where neutrinos quietly turn some protons into neutrons just in time to let the chain sneak past waiting points, building a handful of proton-rich isotopes that other paths miss. In both cases, the rules are simple enough to say aloud to a child. The number of neutrons available, the speed of the outflow, and the time before cooling freezes the pattern. Decide what can be built, and the decision is made in less time than it takes you to breathe. There is a third forge running at the shock front's edge that sounds backward until you picture the environment. In the superheated outer layers, a bath of fierce photons kicks neutrons, or even alpha pieces out of pre-existing heavy nuclei, nudging them toward rarer, proton-rich versions of elements. So even the light in this blast is a sculptor, carving out isotopes that steady fusion could never favor. Add these 3 lines together: explosive rearrangement near the core, neutrino, tuned winds above it, and photon chiseling farther out, and you have a truthful map of how a single dying star can stock a galaxy's shelves, with a surprising range of heavy merchandise in one furious shift. You might be tempted to ask, but didn't you say earlier that some of the very heaviest elements come from different storms? And you would be right to remember that rare collisions of dead stars also forge a great deal of the deep end our process cargo. Honesty does not spoil the wonder here. It sharpens it. The supernova's final blast is the first place the universe learns to make many heavy things quickly and locally, while other, rarer events finish the job in another register. On your desk, the iron in a paperclip, and the calcium in a shell, and part of the nickel in a coin owe their existence to explosive burning behind a shock. The iodine in your salt, and some silver in a ring, may trace to a fast neutron rain in a wind. And certain unusual isotopes are the chisel marks of a photon bath, each route leaving a signature pattern that careful observers can later read. Those receipts are not abstract. They arrive as light curves powered by the decay of a specific nickel forged in the heat of the shock, as spectral lines from expanding gases that reveal which elements sit where by their characteristic colors, as tiny grains in primitive meteorites, whose isotopic accents betray formation in particular layers during the blast, and as odd abundance patterns in the atmospheres of very old stars that remember a single nearby explosion, with a distinctive bias toward, say, strontium and barium, or toward europium, and beyond. Each clue is modest on its own. All of them line up into a calm chorus. Heavy elements are not an idea. They are the ash of specific, time-limited conditions that most stars reach exactly once. What makes this chapter not just informative but quietly moving is how democratic the making is within the chaos. Every factor that seems like noise, small differences in density from place to place, a slightly stronger magnetic field that channels some outflow into a jet, a locally proton-rich pocket where a neutrino flips the odds, becomes a way for the blast to diversify the catalogue of matter. Even the asymmetry that once felt like a nuisance in explosions now reads as a gift, because it mixes layers that a tidy spherical event would have kept apart, letting newly made isotopes hitch rides to the surface they would otherwise never reach. The result is not a homogeneous spray, but a clumpy shipment. And those clumps matter later, because the places that catch a rich knot of iron or oxygen or nickel cool and collapse differently than places that catch more carbon or silicon, turning the chemical map of a region into a weather report for future stars and planets. Keep the physics in your pocket in 3 short rules, and you will never lose the thread. First, heat and squeeze. Fast enough and nuclei resort into iron group and neighbors. Second, bathe seeds in a flood of neutrons or tip the balance with neutrinos, and you can climb well beyond iron in seconds. Third, blast with photons at the edges, and you make rare proton-rich isotopes freeze the scene with rapid expansion, and whatever pattern exists at that moment becomes cargo, not theory. There is a lovely humility in how this knowledge changes your everyday gaze. A gold ring on a hand stops being only a symbol and becomes a receipt from a few milliseconds, when neutrons were plentiful and a seed nucleus accepted them as fast as they arrived. The iodine in table salt stops being just seasoning and becomes a museum tag for a wind that briefly leaned neutron. Wood, a streak of calcium in a rock, becomes a postcard from the layer where the shock first knocked order into a new shape. And iron, so unromantic most days, becomes the quiet confirmation that explosive burning did the heavy lifting just behind the departing shock front. If you want a final image that holds both the science and the feeling, picture a dark warehouse in which 3 machines start at once. When the alarm sounds, a press that crushes parts and refits them, a conveyor where workers slap extra pieces on racing frames, and at the far end, a bright lamp that etches details into finished pieces. The power flickers, the floor shakes, doors fly open, and in under a minute, the output is on trucks and gone, delivered to a city that will build its future from whatever came off those lines. That is the formation of heavy elements in the final blast brief. Decisive, condition, dependent, and endlessly consequential. And when the warehouse doors blow outward into space, the cargo does not simply drift. It begins a long, beautiful journey of mixing and travel that will carry those atoms into new clouds and new worlds. A journey we will follow next as the star's ash spreads across the galaxy and writes its ingredients into places that have not yet learned their names. The spreading of stellar ash across galaxies. If you want to see how one star can change a whole galaxy, don't stare at the flash. Follow the ash. Because the real story begins after the light peak, when the debris of a single death starts a long journey from the shattered star's neighborhood to the broad suburbs of space, and back again. And the path it takes is shaped by a few plane forces working together. Expansion, pressure, turbulence, gravity, starlight, and the invisible push of high-speed particles. First, the debris barrels outward as a hot, fast shell, a shock that rushes through local gas and sweeps it into a growing bubble. And as that bubble expands, it slows, thickens, and cools until it trades speed for structure, piling matter into a rim and leaving a bright, fading interior. A natural sequence you can picture without equations as 3 moods: rush, push, settle. In the rush, small clumps of metal, rich gas outrun the average flow like sparks thrown from a fire. In the push, the shock's pressure chisels the surrounding medium into filaments and sheets. And at the same time, the debris itself is stirred and shredded by instabilities at every boundary. The same way cream swirls and breaks in coffee. In the settle, the shell's cooled skin becomes a place where new chemistry can form on dust grains that condensed from the ejector, turning raw ash into tiny seeds that future clouds will inherit. But the remnant does not live alone. When many massive stars are born close together and die over a short span, Their bubbles overlap and merge into a cavern of hot, thin gas called a superbubble. And superbubbles don't just decorate a galaxy. They vent it, punching tall chimneys through the disk so the mixture of ash and swept up gas can escape upward like smoke from a roof. Depending on how hard the cluster pushes, that flow can rise only a little and rain back down in a graceful galactic fountain. Or it can climb all the way out of the disk and keep going as a wind that carries newly made elements into the galaxy's wide halo and even beyond. Once ash leaves the star's street, the trip becomes a lesson in how different kinds of stuff talk to each other. The hot component, the part that left as a million-degree breeze, fills much of the interior of the superbubble and then leaks into the circumgalactic medium, the vast, dim reservoir that surrounds a galaxy like a hidden sea. There it cools slowly by shining in faint X-ray and ultraviolet light, or it mingles with cooler streams falling in from intergalactic space, creating mixing layers that act like border kitchens, blending recipes from both sides into a new menu of temperatures. The warm component, gas that never got as hot, travels as threads that can be torn, folded, and finally evaporated into the hot phase, unless protected by density or by magnetic fields that drape over each cloud like a net. The coldest component, little knots laced with dust grains, often hitches rides inside the warm flow and survives longer than simple calculations predict. Because the grains radiate heat efficiently, and the clumps can be wrapped by magnetic jackets that slow their unraveling. Starlight adds another hand to the process by pushing on dust. And since dust is mixed with gas like pepper in soup, that push drags gas along too, so radiation pressure helps loft metal-rich material upward in star-forming regions. Meanwhile, cosmic rays, charged particles accelerated by the original shock, thread their way through the gas and act like a diffuse, gentle pressure that can keep a wind going long after the first explosions are done. A quiet engine that needs only a trickle of new fuel from fresh supernovae to stay lit. None of this is tidy, and that's useful. Turbulence born at the edges of bubbles and chimneys mixes ash into its surroundings more efficiently than any smooth flow could. So the galaxy's metallicity, its overall content of heavy elements, rises not as a clean tide but as a patchwork quilt. Richer near star, forming hubs, and poorer in outer districts, over tens to hundreds of millions of years. Those patches blur, but some signatures remain, like gentle gradients that show heavier elements, are more common toward the center in many spirals, because that's where starbirth has been busiest. Yet winds can flatten those gradients by exporting metals outward, and fountains can steepen them by raining enriched gas back down nearer the launch site. The balance is specific to each galaxy's history, which is why two galaxies of the same mass can carry different chemical fingerprints. If you want receipts rather than poetry, the sky offers them in several simple languages. Sideways views of other galaxies reveal dusty, glowing plumes rising from their disks, visual proof that ash is not staying home. Backlit beacons like distant quasars let us read the absorption lines of heavy elements in the halos of foreground galaxies, showing that metals truly reach the outskirts. And close to home, the thin film of gas between stars carries weird, sturdy grains with isotopic accents that betray an origin in specific kinds of stellar deaths, evidence that some ash condenses into solids early, survives the trip, and then seeds later clouds with hard surfaces on which new molecules can assemble. Even the airless moon gives testimony. Micrometeorites, rich in exotic grains, fall there unaltered, reminding us that this reign of history is still ongoing. The fate of dust itself is a miniature version of the larger cycle. Newborn grains condense in the cooling debris and in the outflows of elderly stars, then face a trial by shock as later explosions sputter and shatter them. Some are pulverized back into gas, others are only chipped and later grow again by accreting atoms in calm, dense clouds. As they circulate, these grains become the meeting places where water forms from hydrogen and oxygen, where simple organic molecules begin to practice, where charges dance in starlight to create the faint infrared glow we detect. In this sense, spreading ash is not only about metal numbers, it is about distributing workbenches across a galaxy so that chemistry has places to happen efficiently. Gravity, patient as ever, keeps the overall traffic honest, while winds blow out. Fresh or recycled gas also flows in along the galaxy's invisible highways. And the two motions meet in the halo, where enriched outflows tangle with poorer inflows. The exchanges there decide whether the next generation of stars will be born with a richer pantry or a leaner one, and they set the pace of star formation by determining how much cool gas makes it back to the disk. In a fountain-dominated cycle, much of the ash returns within a few 100 million years and lands not where it started, but downwind, smearing memory along the rotation of the disk. In a wind-dominated cycle, common during starbursts, metals can be lifted so far that they won't come back for ages, if ever, modestly starving the inner galaxy while enriching the space around it. A choice with consequences for the size and speed of future star formation. The educational heart of all this is friendly to hold. Supernovae and stellar winds make bubbles that overlap into chimneys. Ash rides those flows as hot gas, warm threads, cold clumps, and dust. Each with its own survival tricks: starlight and cosmic rays push, gravity and cooling pull, turbulence stirs and magnetic fields guide. Some material escapes to the halo, where it mixes, cools, and sometimes returns as rain. The mixing writes the chemical map that future stars and planets will inherit. Everything else is detail. And yet, there is a human-sized reflection tucked inside the mechanics. Dispersal is not waste. It is preparation. The way a forest fire, terrible up close, returns minerals to soil and opens space for new growth. A galaxy's outflows clear, stir, and fertilize, ensuring that the next round of stars will not be pies of the first but richer, more capable makers. When you hold a stone, a ring, or a glass of water, you are touching matter that rode these winds long before Earth existed. Matter that was shocked, mixed, cooled, and delivered by the quiet collaboration of physics across light years. And if that makes you curious about what comes next, then you're ready to step through the next door, where those returning rains and enriched pockets condense into new stars and planets. And the ash completes its transformation from bright catastrophe to patient builder, the birth of new generation stars and planets. Not every dawn begins with a blaze. Some start as a whisper in a cold cloud. So imagine a patch of the galaxy where the rush of old explosions has grown quiet, and the enriched gas they left behind has cooled and thickened into a dim, mottled loaf of fog. You cannot see much, but you can feel what is now possible in a way it never was before. Tiny grains mix through the cloud act as radiators that let it shed heat. New molecules made from the ashes help it cool even further. And that cooling makes the gas heavier in spirit than in mass, so that gravity's invitation finally outruns pressure's caution. This is the beginning of new generation stars, and the worlds that will gather around them. Second, chances built from seasoned ingredients. And you can follow the birth without any dense vocabulary by keeping a handful of steady ideas in view. Cold gas is easier to gather than warm gas. Roughness helps gathering happen in the right places. And spin does not vanish when things fall, it reorganizes. The roughness comes first. The cloud is not a smooth pillow, but a froth stirred by earlier winds and shocks, with pockets slightly denser than their surroundings. In those pockets, cooling works best, so the gas loses energy and pressure faster than its neighbors. And gravity uses that small head start the way a raindrop uses a speck of dust, pulling in more of what's nearby until the pocket is heavy enough that inward wins over outward. You do not need the formal threshold to feel it. Only the picture of a place where the pull to the center stops being cancelled by the push from within, and a slow, unstoppable settling begins. Invisible magnetic fields thread this fog-like elastic bands. They do not stop collapse, but they slow it and guide it, taking some of the wildness out of the fall. Meanwhile, the same tiny grains that cooled the cloud now help it hide from the glare of nearby stars. So the center can continue cooling as it gathers mass. The result is a core, a dark, dense seed, with a shy spin inherited from the cloud. As the core shrinks, that spin cannot vanish. So the material speeds up the way a twirling dancer does when drawing in her arms, and the fall cannot go straight down anymore. The infalling gas flattens into a swirling disk around a warm, forming star. At this stage, the newborn is called a protostar, and though the label sounds technical, the idea is friendly. The object at the center has not yet lit the long, steady fire we recognize as starlight. It shines because it is being built, gravitational energy turning to heat as matter lands, while the disk feeds it like a river trying to join a lake. Feeding would be chaotic if nature didn't provide a release valve. So along the star's spin axis, magnetic fields act as rails that launch twin jets. Those jets punch holes in the surrounding fog, venting angular momentum and clearing paths that let light escape. If you could see them up close, you would witness narrow beams racing into the darkness and lighting knots where they slam into the medium. Scars of growth, not destruction. Slowly, as the center gains mass and the pressure at its heart rises, the core becomes hot and tight enough to ignite the calm fire of hydrogen fusion, and the star settles onto its long plateau, its light now paid for by joining rather than by falling. That is one half of the story of a stellar nursery, the half that builds the lamp. The other half is the disk, and this is where planets learn to exist. At first, the disk is dust and gas, with dust grains no larger than smoke particles. In the gentle, gas-rich environment, grains bump and stick by electrostatic cling, like ash collecting on a sleeve. They grow into fuzzy clumps, then pebbles, then small stones. The process stutters. Sometimes particles bounce instead of sticking. Sometimes collisions are too fast and shatter what was built. But beyond a certain distance from the star, there is a line, a snow line, where water and some other volatiles are solid. Ice works like glue, making sticking easier, so growth accelerates outside this invisible circle. There, pebbles can collect into dense streams that feel an inward drift through the gas. When the streams become crowded enough, their own gravity wakes up and gathers them into kilometer-scale bodies in a geological blink, a collective leap called an instability in textbooks. And suddenly there are boulders in plain speech. These first solid citizens are planetesimals, and they change the rules because gravity between them is now strong enough to pull from a distance. Some crash and merge, some grind and make fresh pebbles, some settle into calmer orbits. Within a few 100,000 to a few million years, a handful of them in favored lanes become embryos, Moon to Mars in size. By sweeping their neighborhoods, a different growth channel, pebble accretion, lets them gorge efficiently on the drifting small stuff. Either way, the big few get bigger faster, and soon, a disk that began as just gas and specks holds a family of solid seeds. Whether a seed becomes a rocky world or a gas giant depends mainly on timing. If a core becomes several times Earth's mass, while the disk still holds plenty of hydrogen and helium, its gravity can pull in a thick atmosphere and puff it into a miniature star. Siblings. If growth is slower and the gas has already been thinned by the star's radiation and winds, the core keeps only a thin blanket, becoming a super-Earth or a rocky planet. In both cases, the clock is set by how quickly the young star eats and erodes its own disk. Radiation boils gas from the top. The star's wind scours it. Jets carry it off the poles, and forming planets carve lanes that speed the clean-out. So the window for building giants is short, while the window for making rocky worlds is longer. All of this happens while orbits are not fixed. Planets talk to the gas through gravity, raising waves that push back on them. The push can make a young world drift inward or outward, slowly sliding through resonances like a fingertip. Along piano keys, some siblings lock together in neat step patterns that hold for millions of years. Others break free later, when the gas is gone, and their mutual tugs matter more than the vanished cushion, leading to a quiet reshuffling, or sometimes a smash-up that leaves a scar. Even in calm systems, small drifts add up, which is why we find giant planets skimming their stars in some systems, and much farther out in others, and chains of smaller worlds in tight circles elsewhere. Architecture is not a one-size plan. It is the summary of many small pushes and pulls over time. While continents are still imaginary and skies are yet to form, a slower courier service begins its rounds. Icy bodies from beyond the snowline, stirred by the growing giants or by each other, take eccentric paths inward and outward, delivering water and carbon-rich material to rocky cores. Closer to the star, others return to the deep cold, stacking a long-term pantry at the system's edge. The exact mix depends on geometry and on chance. You don't need names to hold the pattern, only the fact that delivery is part of planet making, not an afterthought, and that small couriers accomplish what a disk cannot, moving delicate cargo from where it is stable to where it is useful. As the central star matures from a protostar to a loud, restless youth, its behavior changes the workplace. It rotates fast, crackles with magnetic storms, flares, and emits a harsh wind. That wind and high-energy light gnaw at the disk, until gas in the thinnest regions can no longer hold on and streams away. Photoevaporation, a measured vanishing that begins far out and moves inward. Gaps widen into aisles, aisles into clearings, and finally the gas is mostly gone. What remains are planets, their moons, belts of rubble, and a filigree of dust constantly renewed by gentle collisions. The star's tantrums calm, the wind softens, the light steadies. A planetary system has replaced a construction site. Zoom out and you will see why the second generation is fundamentally different from the first. The material was cooler at the start. The cloud contained efficient coolants and grains, so it fragmented into many seeds instead of a few oversized ones. And around those seeds, disks, formed by the simple preservation of spin. Disks made solid worlds possible because they slowed, organized the fall, turning a chaotic rain into a conveyor. And because the ingredients included carbon, oxygen, silicon, iron, and more, planets could have surfaces, rocks, oceans, and thick or thin atmospheres, none of which the earliest universe could have provided. Planet formation is therefore not an optional flourish, but the natural outcome of a galaxy that has been enriched and cooled by earlier generations. That is why rocky worlds and temperate skies are latecomers, but common latecomers. Once the toolkit exists, nature uses it everywhere. The receipts for this story are modest and reassuring. Baby stars in nearby nebulae still wear disks we can image directly in starlight scattered from dust, or in the faint radio glow of cold grains. And those disks show rings and gaps that trace where young planets are already sculpting lanes. Pencil, beam views through dusty regions, reveal narrow jets and outflows, proof of the angular momentum valves at work. Meteorites in our own system preserve the textures of early melted droplets and the isotopic fingerprints of short-lived radio. Heaters that once warmed them, timestamps for early construction, and sky surveys have found thousands of exoplanets with patterns, resonant chains, hot Jupiters, piles of super-Earths close to their R-stars, that match the predictions of drifting, merging, and timing. None of these clues alone would teach the whole lesson. But together, they hum the same melody. Cold clouds with metals and dust make stars with disks. Disks make planets, and the details depend on the local dance. The gentle reflection tucked inside the mechanics is one you can hold long after the lesson fades. Every world is a specific answer to a set of simple questions. How cold was the birth cloud? How rough? How strong were the fields? How long did the gas last? Who formed first? And who moved where? And those questions are asked and answered again and again across the galaxy. Your sky is not a unique exception. It is one of many completed works in a workshop that never closes. When you drink a glass of water or hold a rock in your hand, You are touching the cool patience of a disk that once hid from the tantrums of a young star, long enough to let solids grow and couriers deliver. And when you look up at night, remember that the stars you see are not only lamps, but also landlords, each with a history of leases and renovations, some with quiet neighborhoods of small, stony worlds, some with giant tenants parked close to the heat, some with families scattered and rearranged by old arguments, all of them shaped by the same few rules and the same long patience. Carry that calm with you, because in the next rooms, we will walk from worlds to the materials that let them host life's chemistry, and the story will narrow from disks and planets to a single element's strange generosity. Carbon's unique role in life. Start with something you can hold: a pencil line, a leaf's edge, the curl in a child's hair. Each is a quiet signature of carbon, an element that behaves less like a single note and more like a whole alphabet. And the reason life prefers it is not mystery or favoritism, but a handful of ordinary habits that together make extraordinary variety possible. Carbon is small enough to sit comfortably in tight molecular spaces, yet strong enough to build frameworks that don't fall apart at room temperature. It makes 4 connections at once, so it can branch like a tree, loop into rings like bracelets, or stretch into ropes and sheets. And those connections can be single bonds that swivel freely for flexibility, double bonds that hold shape for structure, or triple bonds that pack energy for later. With water as life's solvent on a temperate world, that mix is exactly what you want. Sturdy enough to avoid melting into chaos, soft enough to be reshaped by gentle heat and enzymes, capable of dissolving in part of the environment and hiding in another, so that information can be stored, read, and edited without breaking the entire book. In everyday terms, carbon is the best craft wood in the universe's workshop. Cuttable, joinable, sandable, and sealable. While many other elements are either too brittle, too gooey, or unwilling to hold a nail. If you zoom in a little further without drowning in jargon, 3 simple traits explain most of carbon's magic. First, 4 hands. Every carbon atom reaches out in 4 directions, which means you can build 3-dimensional shapes with corners and edges, not just chains. Think ladders, rings, cages, and branching trees. And those shapes matter because function follows form. A protein's fold is a tool's grip. A membrane's kink is a gate's hinge. A hormone's slight twist is a key that fits only one lock. Second, comfortable bonds. The energy of a carbon-carbon or carbon-hydrogen bond is just right. Not so weak that ordinary warmth breaks it. Not so strong that life can't rearrange it with modest effort. That balance lets cells assemble complex molecules and then take them apart again on schedule, releasing energy during metabolism, about as fast as a living body can use it without cooking itself. Third, friendliness with diversity. Carbon gets along with a cast of neighbors: oxygen, nitrogen, hydrogen, phosphorus, sulfur, and the combinations produce functional groups that behave like plug-in parts, alcohol groups that love water, hydrocarbon tails that fear it, amines that act as switches, acids that donate protons, phosphates that move energy around like batteries. With this kit, you can make sugars for short-term fuel and identification tags, lipids for waterproof walls, amino acids for adjustable tools called proteins, and nucleotides for long-term memory we call DNA and RNA, all from rearrangements of the same small inventory. What makes this friendly to remember is that life's big 4 proteins, nucleic acids, lipids, carbohydrates are not 4 unrelated miracles, but 4 different uses of carbon's habits. Proteins are carbon backbones, hung with chemical hands that fold into working shapes. DNA is a carbon phosphate, spine carrying a code on carbon-based letters. Lipids are carbon tails that refuse water and self-assemble into bilayers, making compartments so chemistry can happen in peace. Sugars are carbon rings that store energy and decorate cell surfaces with meaningful patterns. If you can picture beads on strings, rings on rings, and mats of two tailed pins standing shoulder to shoulder. You already see how carbon's four-handedness gives life three basic superpowers: storage, shape, and selective boundary. A frequent question, often asked with a smile, is why not silicon, since it sits below carbon on the periodic table and can also make four bonds? The short, honest answer is that silicon's bonds are clumsier in water, heavier, and less versatile. Silicon-fa-silicon links are weaker, so big frameworks wobble. Silicon-fi-oxygen links are so strong that, in watery settings, chemistry tends to run into rock and stop moving. Simple silicon hydrides are unstable in air and water, breaking into less useful products. Silicon is larger, so tight, precise shapes are harder to achieve, and silicon doesn't form stable double bonds the way carbon does, cutting off a whole branch of flexible designs. None of this says life couldn't exist with silicon somewhere. Somehow only that on temperate, watery worlds like ours, carbon is the superior gymnast, balancing strength with flexibility, stability with reactivity, and information density with editability. Another gentle superpower of carbon is catenation, its willingness to bond to itself over and over, making chains from a few units to thousands. That one habit underwrites everything, from rubbery elastin in your skin to the stretch of a muscle fiber and the spring of a plant stem. By sprinkling in small kinks or bulky side groups, living systems tune the stiffness or softness of these chains, the way a musician tunes strings. And by linking two chains at occasional points, they make gels and scaffolds that are neither liquid nor rock, perfect for tissues that must flex and hold shape at once. If you've ever felt how cartilage resists compression yet returns to form, you've met carbon chemistry as architecture. Carbon also carries a subtler gift-handedness. Many carbon centers are chiral, meaning they can exist in left and right-handed forms that are mirror images but not superimposable. Like your hands, life chose one hand for sugars and the opposite for amino acids. And that consistent choice lets enzymes, protein tools, recognize substrates with exquisite selectivity. If both hands were equally common and used, a cell would lose much of its precision. Carbon makes chirality easy, and chirality makes molecular recognition possible, which is how a single enzyme can find one target among thousands, and how the DNA code can be copied with reliable accuracy at human body temperatures in salty water. That mention of water is not a side note. Carbon's partnership with water is central to why it works so well for life on Earth. Hydrocarbons avoid water, polar carbon compounds embrace it, and molecules with both characters, long carbon tails with polar heads, spontaneously arrange into membranes, the two-layered skins that turn chemistry into inside and outside. No micromanager is needed. Put amphiphiles in water, and vesicles bud off on their own, trapping small cargo. With membranes in place, carbon chemistry can set up gradients, differences in charge and concentration, that power work. And because carbon frameworks tolerate gentle rearrangements, tiny rotary motors and pumps can live in those membranes, moving protons and ions to store and spend energy on demand. The world's simplest battery is a carbon-rich membrane with a proton gradient across it. Life has been running on versions of that battery for billions of years. Energy, in fact, is where carbon shines again. CH and CC bonds store chemical energy at levels that are accessible to enzymes, but not so high that accidental sparks are common. When living cells burn carbon fuels, they most often do it in small steps, passing electrons through a chain of carriers, embedded in carbon-rich proteins and membranes. At each step, a little energy is harvested to pump protons and turn a molecular turbine that makes ATP, the spendable coin of the cell. If you peel away the names, the method is steady and elegant. Move electrons from a high-energy carbon framework to a lower-energy carbon, framework, and use the difference to do work, because carbon chemistry can be reversible with modest pushes. Cells can also go the other way, using light or inorganic energy to fix carbon dioxide back into sugars. So carbon acts as both battery and ledger, charged and discharged over and over without exotic conditions. On the information side, carbon offers dense, stable storage, without the need for extreme cold or pressure. DNA's backbone is a repeating carbon phosphate chain that resists accidental breakage in water, while the letters stack like coins through gentle interactions among flat carbon-rich rings. Those stacks read as code to enzymes that slide along the polymer, and because carbon frameworks allow slight, controllable bends and kinks, entire chapters can be folded, hidden, or exposed with small changes in local chemistry. Epigenetics in plain clothes, proteins read that code and, as carbon-based machines, build other carbon-based machines from amino acid parts, closing a loop that is profound precisely because it is ordinary. Carbon writes, carbon reads, carbon builds, all at room temperatures in salt water, without flames or acids. Carbon's range extends even to solid forms that life doesn't use internally, but that help you remember its versatility. Graphite is soft sheets of carbon sliding over each other. Diamond is carbon in a rigid three-dimensional lattice. Graphene is a single sheet of carbon that conducts electricity and bends without breaking. These forms are not alive, but they show how the same element can be plastic across properties: soft hard, insulating conducting, simply by changing how the bonds are arranged. Life exploits a similar plasticity at a smaller scale: rubbery elastin versus stiff keratin, transparent cornea versus opaque horn, again, by rearranging carbon connections in space. If you worry that all this praise sounds like carbon worship, steady the picture with humility. Context matters. Carbon's brilliance shows most in liquid water, at modest temperatures with a steady supply of other elements and minerals. Move to a world of liquid methane, at -180 degrees Celsius, or to a strong acid ocean, at 400 degrees Celsius, and the ranking of best element for life might change. Our claim here is not that carbon is universally supreme, but that, given Earth-like conditions, it is unmatched in blending structural strength, chemical versatility, and energy tunability, enough to build cells that divide, tissues that heal, and minds that ask questions. The simplest way to carry this, without any chemistry at all, is to hold three friendly sentences: carbon builds frames, carbon stores and trades energy, and carbon encodes and reads information. Stir those three into water. Add a dash of other elements for function, and you have a kitchen where molecules can learn behaviors like copying, catalyzing, and compartmentalizing. From that kitchen, every living thing you know eventually walked out. And as a soft closing thought, consider that calling yourself carbon-based is not a reduction but a kind of belonging. You are a temporary library of carbon stories written in warm salt water, able to repair the letters when they smudge and to revise paragraphs as seasons change. The same flexibility that lets carbon form a leaf's edge lets you form a thought. And the same stability that keeps a shell from dissolving keeps your memories from vanishing overnight. If that invites one more question, let it be about the partner that makes carbon stage possible: water, and how its peculiarities turn chemistry into choreography. A door we will open next, with the same gentle pace. The cosmic origins of water molecules. You think water begins in a cloud or a river, but its story starts far earlier, with two travelers made in different furnaces: hydrogen from the universe's first minutes and oxygen forged later in stars. And the wonder is that these strangers learn to meet, not in oceans first, but in space. In places so cold your breath would freeze, and so thin a single grain of dust can matter. Picture a dark interstellar cloud, where starlight is weak and temperatures fall far below any winter you know. Dust specks float there, like tiny workbenches, and on those benches, the recipe is simple enough to say to a child: an oxygen atom lands, a hydrogen atom lands. They try a few arrangements and, helped by the surface, which holds them long enough to meet, an O forms. And then another hydrogen arrives. And the trio becomes H2O, a molecule that sticks as isto the grain. No flame, no splash, just quiet assembly in the dark. Around you, that means the bulk of water in a galaxy first appears as thin, glassy coatings on dust inside these cold clouds. Coatings we can actually detect because they absorb starlight at a very particular shade, near 3 microns in the infrared, leaving a tiny bite in the spectrum like a fingerprint. As gravity slowly squeezes parts of a cloud, and a young star begins to warm its cradle, those icy mantles evaporate, or are knocked free by gentle shocks, turning into vapor that mixes with the gas and briefly perfumes the nursery with water. If the warming grows, the same vapor can break apart under stronger ultraviolet light and then reform in cycles. A kind of cosmic breathing, but the net effect is a stockpile, ice in the cold, vapor in the warm, that rides along as the nursery becomes a disk around the infant star. Space also offers a second path, where colliding is enough to spark making. When a shock wave plows through a cloud or along the edges of a young outflow, the gas heats just enough that oxygen atoms can react directly with molecular hydrogen in 2 quick steps, first forming OH, then H2O. And as the gas cools, that freshly made water is trapped in the flow or refreezes on dust. We know these shock roots are real, not because we witness them with our eyes, but because they produce distinctive masers, naturally amplified radio whispers at a specific frequency, that astronomers hear like beacons from places where water molecules are both abundant and pumped by collisions. And there is a third quiet factory humming, even in the thinnest space. Ion chemistry, where cosmic rays, energetic particles zipping through the galaxy, strike hydrogen to make H3+, a reactive helper that passes a proton to oxygen to build OH+, and then H2O+, and H3O+, which finally recombines with an electron to release neutral water. This path matters in regions too diffuse for dust chemistry alone. And though the names sound technical, the idea is friendly. Charge lets reactions happen that cold temperatures would otherwise deny. By the time a star's disk has taken shape, all 3 sources, ices from the dark, shock-made vapor from warm seams, and ion-built water, have stocked it with more H2O than your imagination expects. But the disk doesn't keep that water spread evenly. Warmth from the new our star and friction in the gas create a gradient, and beyond a certain radius, the midplane stays cold enough that water freezes onto grains. The famous snow line. Inside the line, water is mostly vapor and takes part in hot chemistry. Outside, water coats solids and makes them sticky, speeding the growth from dust to pebbles and then to planetesimals. This is why the outer regions of disks build big icy bodies efficiently. Ice acts like glue and like ballast, allowing small pieces to survive collisions and keep growing. When measurements image young disks directly, we actually see bright rings and dark gaps that trace where such growth and clearing are happening. A quiet confirmation that water and solids are organizing each other. The origins of water on worlds follow from this partitioning, but do not require you to memorize any catalog. Close to the star, rocky seeds form in a dry neighborhood and later receive deliveries from beyond the snow line. Icy planetesimals and small comets that wander inward as they are nudged by giants and by the gas itself. Farther out, embryos that reach critical size early can drink directly from the disk's hydrogen, helium, to become gas giants, wrapped in thick envelopes, where water is a major ingredient. In both settings, timing is destiny. If the gas clears fast, rocky worlds keep modest atmospheres and rely on ice, bearing couriers. If it lingers, giants grow and rearrange routes for everyone else, changing who receives how much water across thousands of star systems. This timing lottery writes enormous variety. Dry, scorched rocks close to their stars, steamy sub-Neptunes with deep water layers, icy moons, with buried oceans warmed by tides. And all of it flows from how H2O behaves at different temperatures, and how quickly the young star's tantrums blow the gas away. You might ask how much of a planet's water is born there versus delivered. And the honest answer is that both paths can matter. Rock itself can trap water in minerals at high temperature and release some later, and hydrogen from the disk can react with oxygen, rich rocks to make water locally. Meanwhile, the isotopic flavor of water, the ratio of heavy hydrogen to ordinary hydrogen, preserves a memory of formation temperature. So by comparing that ratio in oceans, meteorites, and comets, scientists reconstruct the mix of sources. The big picture stays simple, even as the details are debated. The cold temperatures of deep space favor heavy water enrichment, the warmth near a star dilutes it, and a world's final blend records how much it drank from each bar. Cosmic origins don't stop at disks either. Elderly stars puff out shells where water vapor can form in the outflow. Even around stars that are carbon, rich, ultraviolet light in their winds creates pockets where oxygen and hydrogen can meet, adding to the galaxy's pantry. And in the ejected debris of supernovae, newly minted dust grains offer fresh surfaces for ices once the chaos cools. All these contributions feed the interstellar cycle, where water is made, hidden as ice, revealed as vapor, broken and made again, moving with the gas between clouds, disks, and the wide halo. When we look at a faraway galaxy forming stars in a burst, we see the same cycle running fast. Strong outflows loft water vapor into the galaxy's outskirts, where it cools and falls back later, like rain in a vast invisible weather system. Hold the essence as three friendly sentences. Hydrogen from the early universe and oxygen from stars meet on dust grains in cold clouds to make water ice, shocks, and ion chemistry. Add water where surfaces are scarce or heat is available. In disks, temperature sorts water into vapor inside the snow line and ice outside, shaping how worlds grow and how they inherit their seas. From those rules follow the rivers and rains. You know, not as miracles, but as the oldest habit of the cosmos. A habit that turns thin gas into thick meaning. And in the soft closing of this chapter, let the everyday weight of water feel older than it looks. The sip you take is a blend of ancient roots, molecules knit on grains in a night before our star existed, warmed in a nursery and launched across space, frozen onto pebbles, and delivered to a crust that did not yet have a name. Knowing that does not make the drink less refreshing, it makes it more, because you can taste, if only in imagination, the long patience in every drop, and walk on with a little more care for the thin film of liquid that keeps your world bright. Next, we will narrow that care to the alphabet of life, where these same molecules become the stage for DNA and amino acids to practice, not with slogans, but with gentle, readable steps. The elemental story of DNA and amino acids. Hold a single grain of table salt between your fingers and imagine shrinking down until the grain becomes a country. In that quiet landscape, you would find the same cast of elemental characters that script life's longest sentences: carbon, hydrogen, oxygen, nitrogen, phosphorus, and a cameo from sulfur, arranged not as random gravel, but as purposeful architecture. And the most famous buildings they raise are DNA and proteins, whose bricks are nucleotides and amino acids. The story is simpler than the diagrams suggest. If you meet each piece by its job, a nucleotide is a three-part kit: one phosphate that acts like a clasp, and battery, 1,5, carbon sugar that forms the spine, and one nitrogen, rich base that carries a letter. The phosphate's phosphorus holds several oxygen handles that can link sugars together, forming a chain of phosphodiester bonds that is sturdy in water, yet flexible enough to be edited. The base, flat rings packed with nitrogen, stack like coins and pair across the chain via gentle hydrogen bonds, so the ladder stays zipped yet unzips where needed. Those hydrogen bonds are not glue in the hardware sense. They are handshakes just strong enough to recognize the right partner, weak enough to let go when the cell must copy or repair. Meanwhile, the carbon-based sugars provide the regular spacing that makes pairing reliable, and the phosphate backbone, with its negative charge, keeps the whole polymer friendly to water and resistant to accidental collapse. When two such chains run in opposite directions and wrap into a double helix, you get a device that solves three problems at once: storage, recognition, and copying, all at temperatures and pressures you'd be comfortable living in if you set the chemistry aside and listen. DNA is a quiet invention that turns a small set of elemental habits into memory you can both keep and use. Facing DNA across the workbench is the amino acid, a simpler-looking kit with a surprisingly rich future. One carbon in the center holds a carboxyl group, an amino group, a hydrogen, and a variable side chain that decides personality. Link amino acids head to tail by forming peptide bonds between carboxyl and amino groups, and the chain becomes a polypeptide. Now the side chains meet water, salt, and each other, and the whole string folds into a shape, sometimes a zipper, like helix, sometimes a flat sheet, sometimes a compact, intricate tool. In that folded state, the simplest elements do sophisticated work. Nitrogens donate and accept hydrogen bonds to form scaffolds. Oxygens help hold charged groups and catalyze reactions. Sulfur shows up in cysteine to make disulfide bridges, tiny staples that lock a fold, and in methionine to signal starts and carry methyl groups. The 20 common amino acids are variations on this theme, changing only the side chain's size, charge, and water love. And that modest diversity is enough to build motors, pores, clamps, scissors, and switches from the same alphabet. If DNA is a library of instructions written in 4 letters, proteins are the workshop's tools, built from 20 adjustable parts, each shaped by the same small set of elements, reaching out with predictable tendencies. The most beautiful bridge between these two families is translation, a choreographed handoff where one polymer reads the letters and another polymer grows accordingly. Even here, the elemental logic stays plain. Magnesium ions steady the sharp folds of the ribosome, the factory that does the reading, while phosphate energy packets power the steps. Each tRNA is a small, bent piece of RNA with 2 talents. It recognizes a 3-letter word on the message and presents the matching amino acid. The matching is enforced by shape and charge, not by magic, a snug fit between atoms arranged in space. Hydrogen bonds and salt bridges shepherd the pairing. Water mediates the meetings, and when the ribosome clicks, a new peptide bond forms, releasing a drop of water. A small reminder that life writes new matter by swapping bonds, rather than summoning substance. If you wonder where these building blocks came from before there were cells to make them, the elements themselves offer clues. Nitrogen for bases and amino groups is abundant in space. Carbon and oxygen ride in simple molecules like CO, formaldehyde, and hydrogen cyanide. Phosphorus arrives in minerals and in reactive salts and in cold ices on dust grains. Starlight and particle hits drive reactions that produce nucleobases and amino acids in simple steps. Laboratory simulations that chill thin films and shine ultraviolet light make many of the same molecules we see in meteorites. And those meteorites have delivered amino acids with distinctive isotopic accents to Earth. Little postcards from chemistry that predates oceans. Add to this the wet Faidry cycles of early landscapes that naturally concentrate and link nucleotides into short strands and amino acids into peptides. And you have a stage where the elemental cast can practice long before a full cell exists. Clays and mineral surfaces act as patient hosts, holding monomers close enough to react, while simple amphiphiles, born from the same carbon kit, make bubbles that corral the experiments. So selection can begin. Sequences that happen to bind and stabilize others persist. Folds that help reactions happen appear a little more often. The system drifts from chemistry to protobiology, without needing a miracle. Only repetition, concentration, and time. Two quiet quirks give the story its precision, chirality and base choice. Many amino acids are left or right-handed. Mirror forms like your hands. Life on Earth uses almost exclusively left-handed amino acids and right-handed sugars in nucleic acids. A consistent choice that makes matching and folding precise. How that preference was chosen likely involves small bias. Polarized light in space. Particular mineral faces that favor one hand or self-amplifying reactions that tip a tiny imbalance toward dominance. But once a choice stabilizes, every tool and lock is machined to the same standard, and the whole shop runs more cleanly. Base choice matters too. The quartet A, T, G, C is not the only imaginable set, but it balances stability with recognition and mutability, which is why DNA can store centuries of memory in every cell while still allowing the edits that evolution needs. This elemental framing also explains why errors can be both danger and opportunity. A swapped base changes a hydrogen bond pattern and may alter a protein's shape. A modified amino acid can create a new binding site, repair enzymes, proteins again, scan for mismatches by feeling for tiny bumps in the regular geometry of the helix, fixing many slips, but not all. What survives is tested by the environment, which is simply another way of saying that the universe reads the sentence you wrote and answers with yes, no, or try again. None of this demands dense equations to feel true. It is enough to see that DNA and amino acids arise from ordinary preferences of a few elements in water. Carbon's four hands for frameworks, nitrogen's eagerness to lend and accept, oxygen's sharpness, phosphorus's ability to hold energetic bonds and make charged backbones, sulfur's knack for locks, and hydrogen's smallness, making countless soft connections that sum to strength. Arrange those preferences in space, and you get letters that can recognize each other, and parts that can fold and act. Put letters next to parts, and you get a system that can remember, build, and test its own future, all at the scale of warm ponds and cell-sized rooms. If you want a single image to keep, picture a necklace of sugars and phosphates, carrying a coded row of flat stones, each stone with a distinct face. Across from it runs a matching row that knows which face to meet. Nearby, a string of beads curls into a key that fits a single lock because a pair of sulfurs clasp like fingertips and a few nitrogens and oxygens place tiny magnets in the right spots. This is the quiet physics of your body's words and tools. And as a soft closing thought, let the austerity of that palette comfort you. Life did not require exotic stuff or impossible temperatures. Only 6 common elements learning to cooperate in water, building polymers that can speak to each other. From those polymers came muscle and memory, leaf and lung. And the question rising in you now, the next time you hear the word code, remember that its alphabet is written not in glowing screens, but in carbon rings, phosphate rails, and small hydrogen handshakes. A script the universe can write, wherever the same few ingredients gather and are given time. The scientific basis of We Are Stardust. You don't have to take We Are Stardust on faith. You can hold it the way you hold a smooth stone, by its weight, its texture, and the marks time has left on it. Because the claim rests on multiple, independent measurements that fit together like pieces of a careful puzzle. First, there is the timeline check built into the sky itself, where the faint afterglow of the early universe and the chemistry of untouched gas clouds tell us what the cosmos started with. Mostly hydrogen, a steady share of helium, and only traces of anything else. So anything heavier in your body must have been made later. Second, there is the factory check in living stars, where we read their light with prisms and find the fingerprints of elements in their outer layers, then compare those patterns to the predictions of simple fusion rules in hot interiors. And we confirm the engine because the hour star sends us a second receipt. A steady rain of ghost-like particles born in its core that matches the expected reactions. proof that stars truly turn simple fuel into new matter and light. Third, there is the explosion check, the brief and bright events when massive stars die and their inner products are flung outward. Those light curves behave like lamps powered from within by freshly made, short-lived atoms decaying in sequence, and telescopes have even caught the telltale gamma ray lines from those decays, a chemical signature glowing across space. Fourth, there is the grain check, perhaps the most charming of all. Inside certain ancient meteorites are tiny mineral grains, whose internal ratios of isotopes simply do not match anything formed in our solar system, which means they arrived here already made, little travelers from old stars and blasts. And when we analyze them, their accents point back to specific kinds of parents, calm giant stars puffing soot or violent ends, each with a distinctive chemical style. Fifth, there is the nearby dust check on our own world. Layers on the sea floor and chips from the moon carry atoms that shouldn't exist in nature unless a star died relatively recently and sent dust our way, an ashfall written into rock 6. There is the population check across the Milky Way, where older stars are poor in heavy elements and younger ones are richer, exactly what you would expect if each generation inherits and adds to what the previous one returned. And even within that trend we find elders with odd, heavy element enrichments that match the rare storms needed to build the deepest entries in the periodic table. Seventh, there is the collision check from a different kind of catastrophe, when two dead stellar cores merged and the sky gave us not just light, but also a small tremor in space itself, ripples that arrived with a warm, reddish glow whose spectrum matched the making of very heavy elements, a direct view of one of the forges that fills out the final rows. Eighth, there is the abundance match between the solar system and stars like our star. The overall pattern of elements in meteorites and in our star follows the same curve carved by nuclear rules in furnaces and blasts, a broad fingerprint too specific to be chance. Ninth, there is the body inventory that you can read from a medical textbook. Oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, and trace metals. And every one of those comes with a known origin story in the cosmic factory sequence, from the lightest fuels up, through the more elaborate items stamped in late-life stellar shells or thrown together in the brief heat behind a shock. And 10th, there is the travel and delivery check in young planetary systems, where we no longer guess but actually see disks of dust and gas around baby stars, with rings and gaps where solids are growing, and the dust's composition, rich in the same elements that later make rocks and water, confirms that the ingredients of worlds are indeed recycled. Star products being organized anew. When you stack these lines of evidence, you don't just have a slogan, you have a connected story with tests at every turn. The starting inventory is measured, the engines that change it are directly monitored by their light and their neutrinos. The blasts that spread the results are observed in detail. The returned products are caught as grains, and as rain on the sea floor, the galaxy's age-phase chemistry ladder records the buildup. Over time, the rare heaviest elements are tied to specific, witnessed events. The pattern of abundances matches the simple rules we teach. The raw material of planets is seen in place, and your own chemical makeup sits at the end of that chain, not apart from it. If you prefer a simpler image, think of receipts in different languages that all total to the same amount. Spectra are one language, neutrinos another, meteorite isotopes a third, ocean, floor, atoms a fourth, star, population trends a fifth, gravitational whispers a sixth. None of them alone would convince a careful mind, but together they make a calm, converging case that suits science at its best. You may worry that Stardust sounds like a fuzzy metaphor. The truth is stricter. When you hold a piece of iron or calcium or breathe oxygen, you are using nuclei whose internal structure, the specific number of protons and neutrons, could only have been assembled in environments we know how to name and have now watched in action. There is no alternate warehouse in the cosmos where those nuclei are known to form under steady, ordinary conditions. There are only the hot, dense centers of living stars, their later shells as they age, the brief compression behind a shock, and the rare collisions of dense remnants. That exclusivity is the strength of the claim. And because science values consistency, we also check for places the story might fail. If stars did not truly make what we say they make, we would find modern, our star-like stars whose surfaces contradict the predicted patterns. We do not. If the explosive path were wrong, the rise and fall of supernova light would not track the expected heating from specific isotopes. It does. If heavy elements really needed different factories, we'd still need to explain why the merger of dead stars produced the exact colors and brightness curves of such factories in action. It did if early universe chemistry had started with many heavy elements in hand already. The oldest gas clouds would show it. They don't. What's left is a picture with room for details. How often one event type contributes compared to another. How turbulence stirs the products. How quickly neighborhoods recycle. But with a backbone that is both elegant and tough. Simple rules in hot places. Build new nuclei, violent endings, scatter them. Gravity collects them again, and over time, worlds and bodies inherit the mix. If you let that settle, it does not make you small. It gives you a wider address. Your bones are calcium condensed from stellar shells. Your blood's iron cooled from explosive heat. Your teeth's phosphorus carried in ancient dust. Your breath's oxygen exhaled first, by stars and later by leaves. Even sodium in a tear and iodine in a cell's hormone trace, to specific cosmic workshops to say, "We are stardust," is not to wave at the sky. It is to acknowledge that your daily life is the cooled memory of furnaces and brief storms, that the universe runs honestly and repeatedly. And if there is a gentle comfort tucked inside the measurements, it is this. Belonging is not a story pasted on afterward. It is measured in the light of stars, in grains found in rocks, in faint particles caught underground, in patterns that stretch across a galaxy. The numbers say you are local to the cosmos, not a visitor, and knowing that can soften the edge of the question while keeping its curiosity bright. The way a quiet fact can cradle a restless thought. Comparing the lifespan of humans and stars, you carry more than one clock inside you, a pulse that counts seconds, a circadian rhythm that counts days, a quiet calendar of growth and repair that counts decades, while a star carries a different set entirely. And the first step in comparing human and stellar lifespans is to admit we're switching clocks. Once you do, the contrast stops feeling like a contest between long and short and becomes a lesson in how living systems, biological or astrophysical, budget energy, handle maintenance, and close their stories with legacy size to their scale. A person's life is paced by chemistry that is always negotiating. Cells copy their DNA with remarkable accuracy, but not perfection. Proteins fold and refold. Damaged parts are replaced, and tiny errors slip through. You grow, you stabilize, you gradually trade speed for reliability. You are not a machine aiming for eternity. You are a balancing act in warm salt water, and so longevity depends on care, environment, and the inherited settings for repair. A star's life is paced by a different negotiation. Gravity presses inward, light and heat push outward, and the rate at which a star shines is the truce between those two. From the outside, that truce looks serene, but underneath it is a constant exchange, fuel being transformed into pressure, and light just fast enough to keep collapse at bay. Here is the first shared insight. Neither you nor a star is simply burning through a fixed supply. Both of you are continuously managing a budget. Yours in biochemistry, a star's in fusion with feedback loops that stabilize the middle years and make the endings decisive. Where the rhythms diverge is in how scale changes pace. In human life, larger bodies do not automatically race to the finish. Giants don't live only briefly because they are big. In stellar life, size is destiny in a more dramatic way. The more mass a star gathers at birth, the more intensely its core must work to hold itself up, and the brighter it shines. That brightness is purchased by a faster rate of internal change. So the largest stars, brilliant, blue, white, attention, commanding, are sprinters whose adulthood rushes by, while the smallest, quiet, red, almost stubborn in their steadiness, are slow walkers, likely to outlast not just you, but entire epochs of the cosmos. This is not a moral tale about moderation. It's a structural truth. Gravity scales with mass, pressure must answer, and the thermostat writes the life pace in the core's script. Humans, in turn, are governed by maintenance more than mass, diet, pathogens, stress, social bonds, and small inherited differences in repair enzymes. All these nudge the curve. Longevity for people is a choreography between the body's ability to fix what time phrase and the environment's willingness to let that work proceed. Comparing the arcs is easiest if you temporarily set aside absolute years and measure both lives as fractions of their natural course: infancy, steadiness, and transformation. Your infancy is a flurry of assembly and pruning. A star's is a gathering and warming phase inside a cradle of gas and dust, a slow tightening until the inner room is ready to run on its own. Your steady years are a long plateau of maintenance and learning. A star's steady years are the era when its central fire is calm and predictable, and its outer layers broadcast a color and brightness that change only gradually. Your late years are defined by the body's shifting priorities: reserves conserved, repairs triaged. A star's late years are defined by changing fuel at the center and shifting the work outward, which reshapes its surface, its size, and its temperament. Even if you never learn the astrophysical details, you can feel the parallel. When the core story changes, the exterior must adapt, and that adaptation can make the outer appearance fool you about how close the end is. A massive star approaching its finish may still look vital from far away, because its surface is bright and hot. A human approaching a late milestone may look unchanged from across a room. In both cases, the decisive changes are interior and momentum, rich. Another helpful comparison is how communities mark time. Humans carry cultural lifespans layered on top of biological ones. Stories, skills, and ethics are inherited, revised, sometimes lost, often found again. Your personal end is folded into a longer narrative of family and society. Stars belong to clusters that tell a similar truth. Born in the same cloud, they start together. But the heavier ones rush ahead and end early, while the lighter ones loiter. By looking at a single cluster, you can see many ages at once. Not because their clocks disagree, but because the same starting gun sends runners of different speeds across the same track. Astronomers read these mixed scenes to learn how lifespan depends on birth mass, much as a demographer reads a town's age structure to learn about public health and history. Seen this way, long or short loses its sting. The real question in both arenas is fit. Does the pace match the job? A nerve cell that must hold a memory for a lifetime invests in repairs and signaling stability. A skin cell that must renew a barrier turns over quickly. A small, dim star that must endure invests in frugality. A large, luminous star that must reorganize its surroundings invests in intensity. You learn a quiet lesson from the comparison. Duration is not the only measure of significance. The legacy differs in kind. A person hands forward ideas, kindness, craft, and a genetic thread. A memory that can outlast a single life by moving into other lives. A star hands forward elements and motion: carbon for frameworks, oxygen for breath, calcium for bone, iron for blood, shock waves that compress nearby clouds. And those gifts shape the possibilities for later stars and worlds. Neither legacy is better. Each is appropriate to the maker. On the emotional side, humans feel time. We are built to notice beginnings and endings, anniversaries and seasons. Stars do not feel, but their physics makes them express time through color and flicker, eruption and quieting. In both cases, the end announces itself in new language, the handled pace shift. If you want a single image to anchor the comparison, trade the usual candle metaphor for a pair of gardens. A wildflower that blooms fast and bright and seeds the field before the heat rises. and an oak that grows steadily, reshades the ground and outlasts storms. Both are strategies. Both are necessary for the health of the meadow. The sky, likewise, needs brief blue giants to stir and enrich, and long-lived red dwarfs to keep the lights on across cosmic night. This helps you resist two common mistakes: believing that longer always means more meaningful, and believing that briefer always means wasted. The meadow, like the galaxy, thrives on a mix, and there is a deep comfort in adopting the fractional view for your own days. You cannot choose a star's timescale, but you can choose a star's honesty about pacing. You can ask, in each season, whether your output matches your reserves, and whether your inheritance, skills, care, attention will be usefully distributed when your own light dims. The sky does not moralize, but it models. Stability in the middle comes from feedback that listens. Endings are clearer when the next users of your energy are in view. Set the two lifespans side by side once more, and the lesson is simple enough to be said without numbers. Stars and humans both live by rules that balance force with support, change with continuity, and both write their meaning not only in how long they last, but in what they leave arranged. To compare them well is not to flatten one to the other, but to borrow perspective, learning patience from the slow and urgency from the quick, so that your own finite interval feels neither trivial beside a star, nor unbearably brief. It feels like a fitted piece in a larger pattern. And that recognition, far from draining wonder, makes the steady ticking of your many clocks sound like music that belongs. The universe understanding itself, consciousness, and the cosmos. If you quiet the room inside your head and listen carefully, a simple but astonishing fact steps forward. A small patch of matter has learned to say, "I experience." And that patch is you, which is all we really mean when we say the universe is understanding itself. Some of its atoms have arranged into a living system that builds models of the world of its own modeling. It's the everyday work of a brain made of cells that trade tiny electrical pulses and chemical messages, weaving signals into a single, coherent scene so you can move, choose, and care. And the easiest way to keep this clear is to strip the idea into friendly parts. What consciousness is, what it is for, how it is studied, and why it earns a cosmic place, without turning the cosmos into a person. First, what it is. Not a glow that hovers above the body, but the felt side of certain kinds of information processing. The way it is to be a system when its parts are tightly coordinated. Your eyes, ears, skin, and inner sensors send floods of data. But the brain does not simply receive. It predicts and compares, sending signals downward about what it expects and listening for mismatches coming back up. The picture you see is the current best guess the brain can defend given the noise and the needs of the moment, updated many times a second. And that guess is shaped by attention, which is less a spotlight than a budget. More resources here, fewer there. When the budget is high for a particular pattern, say a face in a crowd, that pattern becomes available to many parts of the brain at once. And you can report it, remember it, and use it to guide action. Researchers call this kind of wide availability a workspace, not to shrink the mystery, but to make it testable. Turn off the workspace by deep anesthesia or certain sleep stages, and vivid experience recedes. Restore it and experience returns. You can watch the handoff in hospital monitors as slow, organized rhythms dissolve into fast integrated patterns when someone wakes. Evidence that consciousness is not a single place, but a style of coordination across many places. Second, what it is for in a moving animal with a limited body and a risky world experience is a compressed summary for control, a way to keep track of what matters right now across many senses and memories, without getting stuck in the details. When you reach for a glass, you are not solving equations for every joint. You are guided by a felt map of space, weight, intent, and safety, a map learned through practice and adjusted on the fly. The feeling of I is part of that control system, a center of gravity for decisions. Not a ghost pulled by strings. The brain builds a model of the body and of the social world, and it labels the model men, so it can keep track of promises and plans. This is why emotions belong in a scientific picture rather than being awkward extras. They are fast valuations that tell the system whether to invest energy, withdraw, comfort, fight, or wait. Without them, choices would be slow and often wrong. In this light, consciousness is not primarily a mirror but a dashboard, tuned by evolution to keep a complex animal alive and learning. Third, how it is studied carefully, because we only have access to our own experience from the inside. Scientists use 3 quiet methods to bridge the gap: correlates, interventions, and reports. Correlates are patterns that consistently accompany conscious states. Interventions are changes that move experience up or down to see which mechanisms matter. Reports are the structured ways we ask people to describe what they notice while we record their brain activity. Illusions are especially useful because they reveal how the brain constructs reality and show which assumptions the system uses to fill gaps. Through these tools, several frameworks have earned their seat at the table. One emphasizes global broadcasting across the cortex. Another emphasizes the degree of interconnection required for rich states. A third emphasizes prediction and error correction. None is the final word, but together they give us a map that improves as techniques sharpen. What matters for you is that consciousness is scientifically approachable without being reduced to a dull list. It is a living frontier like weather once was, before satellites, recognizable and measurable, even as details are debated. Fourth, why the cosmic phrase matters, but must be handled gently. The universe is not awake in the way you are. Rocks do not introspect. Galaxies do not worry. What is true is both humbler and richer. Given time, certain places with the right flows of energy and materials produce organisms that can model their surroundings and themselves. Share those models through language and test them with tools. Minds are emergent pockets, not exceptions to physics, but special arrangements within it, where information is harvested from uncertainty and turned into action and meaning. In physics language, life and mind are dissipative structures that maintain order by dumping entropy into the environment. But you do not need the jargon to hold the heart of it. Thinking is a way of staying coordinated in a changing world. And science is how many minds pool their private pictures into a public one that can be checked. Telescopes and microscopes are extensions of the nervous system. Mathematics is a precise shorthand for patterns. Peer review is a group's way of lowering its own bias. Seen from above, the universe understanding itself is cooperation across scales. Cells to brains, to communities, to instruments. That lets matter reflect on matter, with increasing honesty. A few boundary questions sharpen, rather than blur, the picture. Other animals plainly share portions of this capacity. An octopus solves puzzles with an architecture unlike ours. Corvid's plan. Mammals dream. So consciousness is almost certainly diverse. Not all or nothing. Machines can already recognize patterns and generate answers. Whether they experience is an open, careful question tied to the kinds of integration and embodiment they achieve. Humility is the correct posture here. Avoid both panic and premature certainty. For now, the strongest lesson is that subjective life tracks with rich, integrated, flexible processing in a body that cares about its own persistence. Where does awe fit? Right in the middle. Awe is what you feel when your prediction machinery meets a pattern, too large or too clean for its usual grip. A night sky, a glacier, a newborn's face. And for a moment, the brain loosens the self-story and widens the workspace. Studies find that such moments can make people more generous and less fixated on trivial REITs, which is a practical reason to carry the cosmic view into daily choices. It does not make you small, it restores proportion, reminding you that your worries are real but local, and that your capacity to connect attention, curiosity, kindness, is a limited resource worth spending wisely. Bring the strands together, and a simple, sturdy sentence remains. Consciousness is the felt coordination of a predictive, embodied brain. Knowledge is the community's way of checking its private films against the world, and calling this the universe understanding itself is a poetic but accurate shorthand for matter arranged to make, test, and share models of matter. You are one such arrangement. A temporary observatory where starlight, language, memory, and care meet. If that idea slows your breath and settles your shoulders, let it. Because it suggests a gentle task. Keep your workspace clear enough to learn, your models honest enough to help, and your circle wide enough to include other minds, so that this corner of the universe continues its experiment in understanding with a little more light and a little less noise. The legacy of the first stars, the impossibility of life without them. Try a thought experiment that starts with subtraction. Imagine a universe that never manages its first generation of stars, and immediately the everyday things you rely on fall away. Not because of pessimism, but because of simple cause and effect. Since with no first stars there are no furnaces to forge the elements beyond hydrogen and helium. And without those elements, there is no carbon to sketch flexible molecules, no oxygen to make water or breathe with, no nitrogen for the letters of genes, no silicon and magnesium and calcium to build rocks and shells, no iron to carry oxygen in blood, or to form the cores that shield planets with magnetic fields. From that single removal, follow a cascade of absences that ends very quickly in silence. No dust to cool clouds and seed planets. No solid surfaces to stand on. No oceans to hold heat and chemistry together. No trace metals to catalyze the delicate reactions inside cells. Not even the kind of long-lived, steady stars that give evolution time. Because in a metal-free cosmos, the gas cannot fragment into many small seeds, and the stars that do form tend to be short-lived beacons, glorious, yes, but too brief to host patience. When you reverse the thought experiment and put the first stars back, their legacy becomes obvious, not as poetry, but as infrastructure. The way a city's first wells and roads quietly determine everything that comes later. Their first gift is composition. They fabricate the heavier elements in their cores, and in their changing seasons and final moments release them. That's the chemical spine of habitability, not a flourish. A planet cannot organize a carbon-based biology if the galaxy has never been taught how to make carbon, cannot run membranes or energy transfer without phosphorus and sulfur, cannot assemble enzymes without iron, zinc, copper, and magnesium. Even the clear air and blue sky you take for granted are downstream of earlier stars, because the gases that make them possible include products of stellar alchemy, and the very idea of a mineral depends on a menu of atoms that did not exist at the start. Their second gift is architecture. Heavy elements change the way matter behaves when it cools. With metals present, gas can radiate heat efficiently, fragment into many seeds, and form not only stars of many sizes, but also the flat rotating disks around those stars, where small solids can grow into larger ones. Without that cooling, and without dust, a byproduct of aging and dying stars, there is no gentle path from specks to stones to worlds. And because iron and similar elements make dense cores, they allow planets to generate protective magnetic fields that shield atmospheres from stellar tantrums. Take away the first stars, and you take away the conditions for stable climates and long-lived surfaces where rivers and soils can learn to cycle nutrients. Their third gift is timing. By changing the chemistry of their neighborhoods, the earliest stars widen the range of stars that can form later, including small, steady-hour stars, with lifetimes long enough for biology to try, fail, and try again until mind appears. Untaught gas favors giants that live fast and die early. Taught gas can build quieter lights that leave centuries to complex chemistry and eons to ecology. And when those later, calmer stars host disks, water-rich bodies can migrate and deliver volatiles inward, because outer ices and inner rocks now exist in the same system, thanks to the earlier enrichment. The slow planet making traffic that sets a table for life is therefore not an accident. It's a delayed consequence of the first lights changing what the galaxy can do. Their fourth gift is texture. Explosions and strong winds from early stars stir the surrounding medium, compressing some regions and thinning others, setting up the patchy map on which later clouds condense. That roughness is not cosmetic. It's how you avoid a bland universe, where nothing gathers, density, contrasts, guide where the next generations will take root, even the long, slow recycling between a galaxy and its halo. Material lofted out, and later falling back enriched, begins with those first injections and continues as a kind of weather that carries ingredients to new addresses. The lakes and soils of future worlds are fed by that traffic. If you prefer a checklist to a story, trace any everyday requirement for life back to its source, and you will step through the same door. The periodic table in your kitchen comes from stars. The cooling agents that let clouds collapse into many seeds come from stars. The dust that becomes the seedbed for planets comes from stars. The core metals that power planetary shields come from stars. The nutrient trace elements that make metabolism possible come from stars. The time carved out for slow biological invention is granted by the existence of smaller, steadier. Our stars made possible after enrichment remove the first generation, and each of those pathways snaps. And yet, there is a softer legacy hidden in the practical one. Those early stars do not only hand forward materials and structures, they create the conditions for memory to exist at all. Because complex chemistry requires places to accumulate information. Polymers that can copy with variation, rocks that can record climate swings, oceans that can store heat and salt. None of which is available before the cosmos learns to diversify its matter. Meaning needs memory, and memory needs the workshops that the first stars open. You do not have to lean on grand metaphors to feel the consequence in your own life. The calcium in a tooth, the oxygen in a breath, the phosphate in a thought, the iron that carries that oxygen. All are older than your world. All are the cooled light of early furnaces. The fact that you can ask where you came from depends on a history that delivered not just atoms, but also stable settings, where atoms could organize into questions. So when you hear legacy of the first stars, don't picture a distant museum, picture plumbing, wiring and daylight. The basics without which a house is not a home. Their work is what turned an almost featureless early universe into a place with beaches and forests, with climates and cycles, with chemistry detailed enough to learn, with minds careful enough to wonder. And if that realization carries a gentle obligation, it is only this: to treat the thin film of habitability on our world as a rare inheritance, not a guarantee, and to extend the long patience that built you into the choices you make inside that inheritance, so that the story those first stars began keeps room for listeners yet to arrive.